What if everything you thought you knew about time was wrong? What if the ticking clock, the racing heartbeat, the rise and fall of the sun, the irreversible forward march of life were all illusions? The idea seems strange, almost heretical to our everyday experience. Yet, when we dive into the depths of physics, metaphysics, and the philosophical foundations of reality, we find an unsettling yet fascinating idea. That time might not be real, or at least not in the way we think it is. Welcome to an intellectual journey that spans from Einstein to quantum mechanics, from the deepest insights of human consciousness to the furthest reaches of the universe. Over the next 4 hours, we will explore the most profound and mind-bending ideas ever proposed about time. We begin this odyssey with one of the most radical and elegant concepts in modern physics, the block universe theory. The block universe theory is not a fringe concept from the dusty corners of forgotten academia. No, it is a direct descendant of Einstein's theory of relativity and is respected by many physicists and philosophers alike. Sometimes referred to as the eternalist view of time, the block universe paints a picture of reality in which past, present, and future are equally real and equally existent. In other words, every moment in time, whether it's your birth, this very second, or a distant day in the future, coexists in a four-dimensional structure known as space-time. To truly grasp what the block universe entails, we must first revisit Einstein's revolutionary insights in the early 20th century. In his theory of special relativity, Einstein revealed that space and time are not separate, absolute entities. Instead, they are woven together into a single fabric, space-time. In this fabric, time does not flow the way we experience it. Instead, it's more accurate to think of time as a dimension similar to space. Imagine a loaf of bread, where each slice represents a moment in time. The entirety of the loaf exists all at once. You can cut a slice from the past, the present, or the future, but all slices are part of the loaf. This analogy, while simplistic, illustrates a key aspect of the block universe. All points in time exist simultaneously, though we only experience them sequentially. In this view, change is an illusion. The idea of a now, moving from the past toward the future, is not a feature of reality, but a feature of consciousness. The block universe theory argues that the passage of time is not built into the fabric of the universe. Instead, what exists is a complete, static four-dimensional block containing all events, births, deaths, the formation of stars, the extinction of species, the rise of civilizations, laid out in a timeless structure. The implications are both liberating and disconcerting. If the block universe is correct, then your future is as fixed as your past. Free will may be an illusion. Choice may be a feature of perception, and death may not mean the end in the way we think. After all, if every moment exists eternally in the space-time block, then the moment of your existence is forever etched into reality. But let's go deeper. In everyday life, we distinguish clearly between the past, which we remember, the present, which we experience, and the future, which we anticipate. This experiential asymmetry is deeply rooted in our biology, our language, and our culture. Yet physics tells us that this distinction might be nothing more than a useful illusion. There is no absolute present in Einstein's theory of relativity. Instead, what counts as now depends on your frame of reference, how fast you're moving, and where you are in the gravitational field. This leads us to a peculiar and profound consequence. Simultaneity is relative. Two observers moving at different speeds may disagree on whether two events happened at the same time. This is not a flaw in measurement. It's a fundamental property of space-time itself. So if there's no universal now, then perhaps there's no objective flow of time either. In the block universe, the arrow of time, the direction we feel time moving in, isn't a physical feature of the universe. Instead, it's an emergent property of consciousness and entropy. We'll discuss entropy and thermodynamics later in depth, but for now, let us focus on the deeper philosophical implications. Imagine someone is watching your life from outside the universe. To them, your birth, every decision you've ever made, and even your death are laid out like frames of a film reel. You're not moving through time, you're embedded in it. Just as every location exists in space, every moment of your life exists in time. This perspective is echoed by Hermann Minkowski, Einstein's former teacher, who famously said, "Henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." This union, space-time, is the stage upon which the block universe plays out. But if every event is set in space-time, what does that mean for causality? Are we puppets on a deterministic stage, following a pre-written script we can't see? Or does our consciousness somehow transcend this block, giving us the illusion of freedom? Some physicists and philosophers who support the block universe idea are determinists, believing that everything that has happened is happening and will happen is locked into the fabric of reality. But others propose subtler interpretations, where the future still feels open from our perspective because we don't have access to it yet. In this view, the illusion of time may be like the illusion of color, not an objective property of the universe, but a mental construct generated by our brain in response to stimuli. The block universe has also sparked interest in theological and metaphysical circles. If all moments exist eternally, could this suggest a timeless perspective from which the universe can be observed, a view outside of time that aligns with the concept of an eternal observer, perhaps even a divine one? Or is this simply anthropomorphizing our ignorance? Furthermore, some versions of the block universe, such as the eternal inflation model in cosmology, suggest that not only is our universe a block, but there may be an infinite number of such blocks, each with its own timeline, reality, and laws of physics. This multiverse idea, while speculative, adds yet another layer of complexity to the discussion. Now, let's take a brief pause to reflect on how radically different the block universe is from our intuitive sense of time. We feel time moving. We make plans for the future. We regret the past. We experience time as a river that carries us forward. But according to the block universe, that river is frozen. Every ripple is already in place. Every leaf that falls into it is suspended, unmoving, part of the structure of space-time itself. It's not surprising, then, that many reject the block universe on intuitive grounds. The idea that time doesn't flow seems to contradict everything we know and feel. But remember, much of science contradicts common sense. Quantum particles don't behave like baseballs. Light can be both a particle and a wave. The Earth is round, even though it feels flat. Our senses evolved for survival, not truth. So when our senses and intuition conflict with physics, it's often physics that turns out to be right. There are critics, of course. Some philosophers argue that the block universe undermines our understanding of consciousness, of experience, and of ethical responsibility. If all events are equally real, what becomes a moral action? Does it matter what we choose to do if our choices are already fixed? Or is the experience of making a choice itself part of the block? An illusion, but a necessary one for sentient life? Still, the block universe continues to attract support, particularly from those who embrace a scientific realist view, that the universe is exactly as our best theories describe it, regardless of how it feels. And so, we are left with a picture of reality that is static, eternal, and complete. A universe where nothing is born, nothing dies, and everything just is. But this is only the beginning. Having explored the expansive, four-dimensional structure of the block universe, where past, present, and future exist simultaneously, we now turn to a complementary, yet radically different perspective on the nature of time, one proposed by the British physicist Julian Barbour. His vision is provocative and compelling. Time, as we experience it, might not be fundamental at all. Instead, reality could be understood as a vast collection of timeless nows. Julian Barbour challenges the conventional wisdom that time flows or even exists as a basic element of the universe. In his groundbreaking work, Barbour argues that what we call time is an emergent phenomenon, a byproduct of the relationships among static configurations of the universe. According to him, the universe is best described as a series of distinct, instantaneous snapshots, or nows, each complete and self-contained, without an underlying temporal dimension linking them. To understand Barbour's view, imagine a vast cosmic gallery filled with countless paintings. Each painting depicts a complete state of the universe, a configuration of all matter and energy at an instant. However, unlike a movie, these paintings are not arranged along a timeline. Instead, each now exists timelessly and independently, without a real before or after. What we interpret as the flow of time is our consciousness moving, or more accurately, jumping through these snapshots. Barbour calls this collection of timeless moments Platonia, a timeless realm of all possible configurations of the universe. In Platonia, time is absent. Only nows exist complete and whole. Our sense of motion, change, and causality arises from the similarity between adjacent nows. If two snapshots are nearly identical except for a slight difference, a star shifting its position, a leaf falling, our brain interprets this as the passage of time. This radical idea stems from Barbour's attempts to reconcile quantum mechanics and general relativity, two pillars of modern physics that notoriously clash in their treatment of time. While relativity treats time as a dimension intertwined with space, quantum theory suggests time is an external parameter, flowing independently of the system being observed. Barbour's timeless physics attempts to dissolve this contradiction by removing time altogether from the fundamental description of reality. How can this be possible? How can a universe without time produce our rich temporal experience? Barbour argues that the key lies in what he terms time capsules. These are special configurations of the universe that contain records, memories, fossils, photographs, or any form of physical evidence that create the appearance of a consistent history. In a now that includes a fossil, that fossil points backward to another now where a creature lived. Our brain interprets this as a past event, even though both nows coexist timelessly and independently in Platonia. In this framework, the illusion of time's flow is an emergent feature arising from the internal structure of individual nows. These time capsules provide a kind of internal ordering, making certain snapshots seem earlier or later, even though, fundamentally, there is no before or after. One might ask, if time is not fundamental, what about change? Barbour suggests that change is nothing more than a difference in the configuration of the universe between one now and another. There is no underlying river of time. Rather, there are distinct islands of existence, each complete in itself. The experience of motion is the brain's way of linking these islands by noticing similarities and differences. Barbour's ideas echo the ancient philosophical position of Parmenides, who argued that change is illusory and that reality is eternal and unchanging. Yet, Barbour's approach is firmly rooted in modern physics, and he supports it with detailed mathematical formulations. His 1999 book, The End of Time, presents a comprehensive argument for this timeless perspective. Barbour delves into the Wheeler-DeWitt equation, a fundamental equation in quantum gravity that lacks a time variable entirely, indicating that time might not be part of the universe's fundamental fabric. According to Barbour, this suggests that the universe is described by a timeless quantum state, reinforcing his vision of a timeless reality. The implications of Barbour's timeless physics are profound. If time is emergent and not fundamental, then the nature of causality, free will, and even consciousness may need to be reconsidered. Our entire experience of life, a continuous stream of moments, could be a construction of the brain interpreting static snapshots. Yet, Barbour's model doesn't deny the existence of our experiences or memories. Instead, it locates their origin in the intrinsic structure of these nows. Memories are simply physical configurations within snapshots, creating the impression of temporal sequences. Critics of Barbour's view argue that while it may work mathematically, it struggles to account for the undeniable experience of temporal flow and the arrow of time. the one-way direction in which events unfold, linked closely with entropy and thermodynamics. They question whether the illusion of time's flow is sufficient to explain phenomena like aging, decision-making, or the second law of thermodynamics. Still, the idea that time might not be a fundamental backdrop, but a derived concept continues to gain traction, especially among physicists working at the intersection of quantum gravity and cosmology. Barbour's vision invites us to rethink our most basic assumptions about the universe and to consider that the flow of time might be more about perception than physics. As we contemplate Barbour's timeless nows, the question arises, if time is not fundamental, what then is? Is there a deeper layer of reality beneath our experience, perhaps defined by relationships, information, or geometry? And if so, could our consciousness itself be something outside time, a spark that stitches together static moments into a continuous story? These questions lead us naturally to another powerful view of time, known as the B theory of time, which challenges the notion of temporal becoming and instead treats time as an ordered dimension without objective flow. Continuing our deep dive into the nature of time, we now explore the B theory of time, a philosophical and physical perspective that, like Julian Barbour's timeless physics, questions the very passage of time. The B theory of time, sometimes called the block view or tenseless theory, suggests that all events in the universe, past, present, and future, are equally real and fixed within a four-dimensional structure known as space-time. According to this theory, time does not flow or pass in any objective sense. Instead, the distinctions between past, present, and future are subjective, dependent on the observer's viewpoint. This contrasts sharply with what is known as a theory of time, or Presentism, which asserts that only the present moment truly exists, and the past is gone while the future is yet to come. The roots of B theory trace back to philosophers like J.M.E. McTaggart, who in his famous 1908 paper argued that time is unreal because the notions of past, present, and future are contradictory. While McTaggart himself concluded time was an illusion, later philosophers refined this into B theory, which embraces the reality of all points in time but denies temporal passage. In the B theory, time is treated much like space. Just as all places in space exist regardless of whether we are at one particular location, all points in time exist in a tenseless manner. Events do not move from future to past. They simply are. Your birth, your current reading of this script, and your future experiences all coexist in the temporal dimension. To visualize this, imagine a book. Each page represents an event in time. The pages are laid out in a fixed order. From the perspective of the book as an object, all pages exist simultaneously. There is no inherent now page that moves from the front to the back. Our experience of turning pages, of moving from one event to another, is analogous to our consciousness moving through the block universe. Physicists often associate B theory with Einstein's theory of relativity. In relativity, there is no universal now. Different observers moving relative to each other can disagree on the simultaneity of events. What is now for one observer may be past or future for another. This relativity of simultaneity undermines the idea of an objective flowing present, aligning naturally with the B theory view that all times exist equally. The B theory also provides a framework to understand causality without relying on a flowing time. Instead of cause and effect being linked by a dynamic passing of time, they're connected by a fixed sequence of events within the block universe. This fixed sequence respects the light cone structure of space-time. Causes must lie in the past light cone of effects, ensuring consistent causation without invoking the flow of time. Yet if time does not truly pass, why do we feel the arrow of time, the sensation that moments flow and that the present is unique? B theorists explain this subjective impression as emerging from the structure of the block universe itself. Our brains are embedded within this space-time block and process information sequentially, creating the sensation of change and flow. Memory plays a critical role. We remember past events, but not future ones, giving a directional bias to our experience. Furthermore, The thermodynamic arrow of time, the increase of entropy, provides a physical basis for this directionality. While the entire space-time block is fixed, entropy increases monotonically along the temporal dimension, marking a clear direction within the block. Our experience of time's passage aligns with this entropy gradient. Critically, the B theory of time preserves the objective reality of all moments while explaining away the flow of time as a cognitive phenomenon. This resolves many philosophical puzzles, such as how to reconcile free will with a deterministic universe. If all events are fixed in the block, the notion of making choices can be reinterpreted as our consciousness locating itself in a particular sequence of events. However, this also raises profound questions. If future events already exist, what does it mean to act freely? Is the future predetermined, or is there room for genuine novelty? And how does consciousness experience only one moment at a time in a fixed block? Physicists and philosophers continue to debate these questions. Some argue that B theory, while elegant, fails to capture the fullness of human temporal experience. Others embrace it as the most consistent interpretation of modern physics. The B theory stands as a compelling challenge to our everyday intuition of time as something that flows. Instead, it suggests that time is more like a dimension of space, one where every event is laid out, fixed, and eternal. From this vantage point, the passage of time might be a feature of our minds rather than the external world, echoing ideas found in Barbour's timeless physics, but framed differently, less about discrete nows and more about the tenseless totality of space-time events. This profound shift invites us to rethink not only physics, but the nature of existence, identity, and consciousness. As we explore further, we will find other theories that propose different radical reimaginings of time, some emphasizing relativity, others emerging from quantum mechanics, and some from even more abstract principles. Time as a human construct challenges the deeply ingrained notion that time exists as an independent, objective feature of the universe. Instead, this perspective proposes that time is fundamentally a mental model, an invented framework that our brains use to interpret and organize the continuous flux of change we perceive around us. It is not a property existing out there in the world, but a cognitive tool designed to make sense of experiences, memories, and expectations. From this viewpoint, the passing of time does not reflect a physical movement or flow, but rather the way consciousness sequences events and orders phenomena. Our perception of past, present, and future arises because the brain sorts and encodes sensory information, creating a narrative that allows us to predict, plan, and react. Without this mental organization, the raw data of reality, sensations, events, and interactions would be a chaotic jumble, lacking coherent structure. The psychological construction of time is closely tied to memory and anticipation. We remember past experiences and imagine future possibilities, weaving them together into a coherent story. This narrative continuity, essential for identity and survival, requires a temporal framework that situates moments in relation to one another. The brain essentially projects time as a dimension, carving a linear path through the ever-changing present. Research in neuroscience supports this conception by demonstrating that the brain's internal clocks and temporal perception are influenced by attention, emotion, and context. For example, moments of intense fear or joy can seem to dilate or contract time, revealing that our experience of duration is malleable and subjective. Furthermore, studies show that different species perceive and process time differently, indicating that temporal experience depends on the specific neural architecture and evolutionary pressures rather than any universal physical property. Philosophically, this approach aligns with anti-realist or constructivist theories, which hold that certain concepts, including time, exist primarily in the mind rather than as entities independent of observers. It suggests that the objective universe may be timeless or at least not structured according to the temporal categories that humans impose upon it. If time is indeed a mental construct, then questions about its ultimate nature may be reframed. Instead of asking, "What is time?" we might ask, "What does the brain create the experience of time?" This shift places emphasis on consciousness and cognition, exploring how internal processes shape our reality. Yet, this view faces significant challenges. Physical theories, such as relativity and quantum mechanics, treat time as an essential parameter or dimension within mathematical models. Clocks measure intervals, particles evolve, and entropy increases, all governed by temporal variables. To reconcile the mental construct hypothesis with physics, some propose that the temporal structures of the universe are not fundamentally temporal, but appear so due to the way observers interact with and measure them. The idea that time is a mental model also connects with cultural and linguistic differences in temporal concepts. Different languages and societies conceptualize time uniquely, underscoring that time's experience depends on mental frameworks rather than fixed external properties. Ultimately, if time is a construct of the mind, it suggests that the flow of time, the arrow of time, and the distinction between past, present, and future are emergent phenomena rooted in how intelligent beings process change. This opens fascinating questions about whether entities without consciousness experience time at all, or if time is meaningless outside of cognitive interpretation. In this way, the human construct theory profoundly challenges classical physics and common sense alike, forcing us to reconsider the role of the observer not just in measuring time, but in bringing it into existence in a meaningful way. Moving forward, we can explore the relativity of simultaneity, a concept from Einstein's theory of relativity that further complicates our understanding of time by showing how the notion of a shared present moment breaks down. Even more so, reinforcing the idea that time may not be absolute or universal. Relativity of simultaneity fundamentally transforms our understanding of time by revealing that the concept of a universal now, a single, shared present moment experienced identically by all observers, is an illusion. According to Einstein's special theory of relativity, simultaneity is not absolute but relative. Different observers, moving at different velocities or positioned differently in a gravitational field, can disagree on whether two events occur at the same time. Imagine two lightning strikes happening at opposite ends of a moving train. An observer standing on the platform might see both strikes as simultaneous, while a passenger on the moving train could perceive one strike as occurring before the other. Both perspectives are correct within their own frames of reference, demonstrating that simultaneity depends on the observer's state of motion. This relativity shatters the classical notion that time flows uniformly and that there is a single objective present cutting across the universe. Instead, what counts as now depends on who is observing and from where. The absence of a universal present means that past, present, and future are not absolute categories, but vary with the observer's frame. This concept challenges everyday intuition, but aligns with the four-dimensional space-time model, where time and space are interwoven into a single fabric. Events exist within this continuum, and each observer's experience of time slices through it differently. This perspective complements the block universe view, suggesting that all moments, past, present, and future, exist equally, with now being observer-dependent. Relativity of simultaneity has profound implications for causality and the nature of reality. It prohibits faster-than-light communication because such signals could create causal paradoxes where effects precede causes in some frames. It also implies that time ordering of distant events is not absolute. Only the causal sequence of events connected by light signals is invariant. This insight forces a reevaluation of time's flow. If no universal present exists, then the idea of a moving now sweeping across the cosmos is untenable. Instead, the flow of time becomes a localized phenomenon tied to an observer's specific frame of reference. Moreover, relativity reveals that time is intertwined with space, forming a four-dimensional continuum. Events do not simply occur in time. They occupy positions in space-time. Time, then, is treated mathematically as a dimension similar to space, but with a unique signature that differentiates it. This relativity of simultaneity supports the notion that time is not an independent entity, but deeply connected to the observer and their motion, reinforcing theories that question the objectivity or fundamentality of time itself. As we proceed, we will delve into quantum timelessness, where quantum mechanics introduces further challenges to our classical understanding of time, suggesting that at the smallest scales, time may lose its conventional meaning altogether. Quantum timelessness presents one of the most profound challenges to our conventional understanding of time by highlighting how, at the quantum level, the familiar notion of time can disappear entirely from fundamental equations. In classical physics, time serves as a parameter that orders events and allows us to describe the evolution of systems. However, in quantum mechanics, especially in attempts to formulate a theory of quantum gravity, the role of time becomes far less clear and sometimes vanishes from the fundamental equations altogether. One of the key pieces of evidence for this is the Wheeler-DeWitt equation, an equation arising in quantum gravity that attempts to describe the wave function of the entire universe. Unlike the Schrödinger equation in standard quantum mechanics, which explicitly includes time as a parameter describing how a quantum state evolves, the Wheeler-DeWitt equation conspicuously lacks any time variable. This frozen formalism suggests that, at the deepest level, the universe's fundamental description is timeless. But how can the universe appear to change and evolve if time is absent at its core? This is one of the central puzzles of quantum timelessness. The answer may lie in how observers emerge and perceive sequences of events within this timeless framework. The apparent flow of time could be an emergent phenomenon arising from correlations within a timeless quantum state. In other words, what we interpret as the passage of time might be a pattern formed by entangled subsystems that define a relational before and after without invoking an absolute temporal parameter. This relational view aligns with the Page-Wooters mechanism, a theoretical model proposing that time arises from correlations between quantum subsystems. In this approach, one part of the system acts as a clock while the rest evolves relative to it. The global quantum state remains static and timeless, but subsystems can exhibit an effective dynamic behavior. Thus, time is not fundamental, but emerges from the internal relationships within the universe's quantum state. Quantum timelessness also brings into focus the problem of measurement and the observer's role in quantum theory. Since time is closely tied to change and observation, the timeless nature of the underlying equations raises deep questions about how conscious experience and classical reality emerge from a fundamentally timeless quantum substrate. Furthermore, the problem of time in quantum gravity highlights the tension between general relativity and quantum mechanics. General relativity treats time as part of the dynamic geometry of space-time, while quantum mechanics traditionally requires an external, fixed-time parameter. Reconciling these perspectives demands a radical rethinking of what time is, possibly moving toward the idea that time is not fundamental but emergent. The implications of quantum timelessness extend beyond physics into philosophy and metaphysics. If time is not a fundamental property of the universe, then notions of causality, change, and history require reinterpretation. The entire concept of a dynamic universe flowing through time might be an emergent illusion, masking a timeless, unchanging reality beneath. Experimental tests of quantum timelessness are extraordinarily challenging, as the scales at which these effects manifest are typically at the Planck scale, far beyond current technological reach. However, theoretical progress continues, and some interpretations suggest that phenomena like entanglement, decoherence, and quantum cosmology may offer indirect evidence. In summary, quantum timelessness forces us to confront the possibility that time, as we experience it, does not exist at the most fundamental level of physical reality. Instead, it might be a derived concept emerging from the complex internal relations of a timeless quantum state. Next, we will examine the emergent time hypothesis, which builds on these ideas by proposing that time arises from deeper, timeless laws of physics through complex collective behavior and relationships. The emergent time hypothesis posits a radical, yet increasingly compelling vision of time, not as a fundamental backdrop against which events unfold, but as a phenomenon that arises from more primitive, timeless physical processes at deeper levels of reality. This hypothesis challenges the conventional picture of time as a universal and ever-present dimension, instead suggesting that what we experience as the flow of time is a macroscopic, emergent feature, much like temperature emerges from the collective motion of microscopic particles, or how fluid dynamics emerges from the interactions of individual molecules. At the most fundamental level, reality may be governed by laws and structures that do not include time at all. Rather, time appears as an effective, large-scale description that organizes our experience of change. One way to conceptualize emergent time is to think of it as a pattern formed by correlations between different parts of a system, a collective behavior that arises from a network of interactions that themselves are timeless. In this sense, time is not embedded in the underlying equations, but surfaces only when we look at the system from a higher level of complexity. This means that the arrow of time, the distinction between past and future, and the continuous passage of moments could be the products of coarse graining, where the fine details of microscopic physics give way to smooth, continuous time at the scale of everyday experience. This view is supported by research in quantum gravity, where attempts to merge quantum mechanics and general relativity frequently lead to models without a fundamental time parameter. The challenge, then, is to explain how the familiar temporal dimension emerges from a timeless quantum geometry or a spin network, as suggested in loop quantum gravity. Here, time can be seen as an approximate, effective parameter that arises in a semi-classical limit, where quantum states of geometry behave in ways that resemble classical space-time. This transition from timeless quantum states to the emergent experience of time could be analogous to how sound waves emerge from the collective vibrations of air molecules, even though no individual molecule carries the property of sound on its own. Thermodynamics also plays a crucial role in the emergent time picture. The second law of thermodynamics, with its inexorable increase of entropy, provide the natural arrow of time and a directionality that distinguishes past from future. Entropy, understood as the measure of disorder or information content, increases because the universe started in a low-entropy state. The emergent time hypothesis suggests that this thermodynamic arrow is not fundamental but arises from statistical properties of the underlying timeless substrate. The growth of entropy might be the macroscopic hallmark of deeper, time-independent laws manifesting through complex systems. Moreover, emergent time opens the door to new perspectives on consciousness and the experience of temporal flow. If time is not a fundamental entity, but arises from complex interactions within physical systems, it could also be linked to how observers, especially conscious beings, process and interpret information. Our brains, by encoding sequences of events and creating causal narratives, might play a pivotal role in giving rise to the phenomenology of time. This aligns with the idea that time is at least partly a construct of the mind, emerging from the interplay between physical processes and cognitive structures. The emergent time hypothesis also encourages a reconsideration of causality and the very structure of physical laws. If time emerges rather than exists fundamentally, then causal relationships themselves might be emergent, approximate patterns rather than absolute truths. This challenges the classical worldview that events unfold in a strict temporal order and suggests instead a richer, more flexible framework where temporal order is context-dependent and observer-relative. This idea is not merely philosophical speculation, but has tangible implications for physics, cosmology, and the quest for a theory of everything. It prompts new research into how timeless mathematical structures can give rise to space-time and how physical processes can generate the effective experience of time. It also calls for novel experiments and theoretical tools to probe the boundary between timeless microphysics and emergent macroscopic time. In the grand tapestry of ideas about time, the emergent time hypothesis stands out by bridging the gap between timeless fundamental laws and the dynamic, flowing time of our lived experience. It suggests that what we call time is a beautiful, intricate phenomenon born from the collective behavior of a timeless substratum, an idea that radically reshapes our understanding of reality itself. Following this, we will explore Presentism, the philosophical doctrine that only the present moment is real, providing a stark contrast to many of the timeless or block universe views and opening a different line of inquiry into the nature of temporal existence. Presentism is a philosophical and metaphysical view about the nature of time that asserts that only the present moment truly exists. According to Presentism, the past is no longer real because it has ceased to exist, and the future is not yet real because it has not come into existence. The only ontologically real slice of time is the immediate present, the now. This perspective sharply contrasts with eternalist views such as the block universe theory, which hold that past, present, and future all equally exist in a four-dimensional space-time manifold. Presentism insists that reality is dynamic and ever-changing, with the flow of time corresponding to the coming into and going out of existence of events. The past is fixed and gone. The future is open and unknown, and only the fleeting present has true being. At its core, Presentism aligns closely with our intuitive experience of time. We live moment to moment, constantly aware of the present and conscious of the passage from past memories to future anticipations. The flow of time is a fundamental aspect of human life, and Presentism captures this phenomenological aspect by positing that only the immediate present moment is ontologically significant. It insists that the past and future are useful concepts, constructed through memory and anticipation, but they do not possess independent reality beyond the present consciousness. This makes Presentism deeply tied to the human experience of temporality, grounding the metaphysical debate in lived reality. However, Presentism faces significant challenges when confronted with modern physics, especially the theory of relativity. Relativity introduces the relativity of simultaneity, which implies that different observers moving relative to one another can disagree on which events are simultaneous, and thus what counts as the present. This complicates Presentism's claim of a single, objective present moment existing independently of observers. If the notion of now is observer-dependent, can there be a universal present that everyone agrees upon? Presentists have proposed various responses, such as adopting a privileged frame of reference or reinterpreting simultaneity, but these remain contentious and are often seen as contrived in the light of relativity. Philosophers defending Presentism argue that the flow of time and the reality of the present moment are fundamental features that any coherent metaphysics must accommodate. For them, the block universe's tenseless view of time, where past, present, and future exist equally and time is static, fails to capture the essential dynamic character of reality as we experience it. Presentism emphasizes the ontological priority of becoming, that things come into being and pass out of being over the static being of all moments in a block universe. In this way, Presentism underscores the significance of change, causality, and temporal passage as primary aspects of reality. Another strength of Presentism lies in its connection to the philosophy of temporal experience and consciousness. Human awareness seems fundamentally oriented towards the present moment. Our memories reach into the past, and our plans project into the future, but our conscious engagement is always with the now. Presentism, therefore, provides a metaphysical framework that resonates closely with the neuroscience of perception and cognition, suggesting that the flow of time corresponds to the succession of conscious moments, each real in its own right. It reinforces the idea that time is not just a dimension like space, but intimately connected to awareness and existence itself. Yet, Presentism must grapple with explaining how change and causal relations occur if only the present exists. How can past causes influence present effects if the past no longer exists? This leads presentists to complex accounts of causation, often appealing to a series of present moments linked by causal continuity. They argue that the causal efficacy of the past is preserved in the traces and effects that remain in the present, even if the past itself is ontologically absent. The future, though unreal, is open and contingent, a domain of possibilities that can only be realized through present actions. In cosmology and physics, Presentism struggles to align with the four-dimensional space-time of general relativity, where time is treated as a dimension similar to space, and all events in space-time exist together in a block. However, some philosophers and physicists propose reformulations of Presentism compatible with relativity, for instance, by suggesting a preferred foliation of space-time that singles out a universal present. These approaches attempt to reconcile Presentism with the empirical success of relativity, but they often require additional structure that is not evident in current physical theories. Presentism also impacts how we think about the metaphysics of identity and persistence through time. Since only the present exists, objects and persons do not endure by being wholly present at multiple times. Instead, they exist at each present moment anew, leading to theories of perdurance or stage theory, where entities are momentary stages linked by relations of temporal continuity. This perspective reshapes classical ideas about persistence, challenging the notion of a stable, enduring self across time, and emphasizing a constantly renewing present existence. Ethically and existentially, Presentism carries profound implications. If only the present is real, it highlights the urgency and significance of our current actions, grounding moral responsibility in the immediacy of now. The past, though gone, shapes us through memory and tradition, but it is the present decisions that truly matter. Similarly, the future, while uncertain and unreal, motivates hope and aspiration, but these must be enacted in the present to have meaning. Presentism thus captures a deeply humanistic and existential view of time as a fleeting yet vital reality. The doctrine of Presentism also intertwines with theological and metaphysical debates. For some philosophies, the present moment is where divine action and human freedom occur. Presentism supports the idea of a dynamic, unfolding creation rather than a fixed, eternal block of time, allowing space for free will and temporal openness. Conversely, it contrasts with fatalistic or deterministic views implied by eternalism, where past, present, and future are equally fixed and unalterable. Interestingly, Presentism influences how we understand memory and historical knowledge. If the past no longer exists, our access to it is indirect, mediated by present records, memories, and interpretations. This raises questions about the nature of historical truth and the reliability of memory. Presentism emphasizes the active role of the present mind in constructing narratives about the past, highlighting the fluid and interpretive nature of historical knowledge. Critics of Presentism often point out that it relies heavily on metaphysical assumptions not supported by empirical evidence. The relativistic structure of space-time challenges the notion of an objective present, and the success of physical theories treating time as a dimension undermines the presentist view. Moreover, some argue that Presentism fails to provide a clear and consistent account of temporal experience and change, which are better captured by tenseless theories of time. Nonetheless, Presentism remains an influential and widely discussed position in the philosophy of time. It resonates deeply with our everyday experience of temporal flow and change, offering a metaphysical framework that prioritizes becoming and the reality of the now. The tension between Presentism and eternalism reflects a fundamental divide in how we understand time, reality, and our place within the universe. In the next part, we will transition to the growing block universe theory, which offers a middle ground between Presentism and eternalism by positing that the past and present are real, but the future is not yet real, thus introducing a dynamic but partially fixed temporal ontology. This theory attempts to reconcile the intuitive flow of time with the existence of a concrete past, challenging both the static block universe and the strictly presentist views. The growing block universe theory offers a fascinating middle ground in the ongoing philosophical and scientific discourse about the nature of time. Unlike Presentism, which holds that only the present exists, or eternalism, which claims that past, present, and future all equally exist, the growing block universe posits that the past and present are real, but the future is not. According to this theory, the universe is like a growing block of space-time, continually expanding as new moments are added to reality. The present is the leading edge of this block, constantly extending as time progresses, while the past is a fixed, concrete entity already incorporated into the block. The future, in contrast, remains unreal until it becomes present and thus part of the block. This view attempts to accommodate the intuition of temporal flow while preserving a robust ontological status for the past. One of the most compelling aspects of the growing block universe is how it captures the dynamic experience of time's passage. In this model, the passage of time is not an illusion, as some eternalists argue, but an objective feature of reality. The universe genuinely grows, and with each new present moment, reality expands. The flow of time corresponds to this growth, providing an ontological basis for the succession of events. This makes the growing block universe attractive to those who want to reconcile the apparent flow of time with a scientifically grounded metaphysics, allowing for both change and permanence within a coherent framework. The idea of the past and present being real while the future is not raises intriguing questions about the nature of causality and determinism. Since the past and present exist concretely, they form a fixed record of events that have happened. The future, however, remains open and indeterminate, allowing for genuine novelty and the possibility of free will. In this respect, the growing block universe aligns with a libertarian view of freedom, where the future is not predetermined by the past and can unfold in multiple ways. This indeterminacy of the future contrasts with eternalism's fixed block, where all times exist equally, implying a form of temporal determinism. Philosophically, the growing block universe bridges the gap between the tenseless and tense theories of time. It affirms the reality of the now and the past, accommodating the subjective experience of temporal becoming, but rejects the existence of a fully determinate future. This helps explain why we have memories of the past and why we feel the passage of time, while also acknowledging the unpredictability and openness of what lies ahead. The theory preserves a sense of temporal asymmetry. The past is fixed and unchangeable, but the future is fluid and subject to causal influence. One challenge for the growing block universe concerns the ontological status of the present. If the block is continually growing, the present moment marks the boundary between the known, real past and the unknown, unreal future. But what makes the present ontologically special? Why does the now have this privileged status as the edge of the growing block? Some proponents argue that the present is where the universe is actively being built, a frontier of becoming. Others suggest that consciousness itself is tied to the present, experiencing the world at this moving boundary. However, these explanations are still debated, and the nature of the present remains one of the thorniest questions in temporal metaphysics. The growing block universe also has implications for physics, especially when considered alongside relativity. The theory tends to assume a universal present that separates the real past from the unreal future. But special relativity's relativity of simultaneity complicates this picture, as different observers moving relative to one another disagree on which events are present. To maintain the growing block view, some theorists introduce a preferred foliation or slicing of space-time to define a global present, though this goes against the spirit of relativity's symmetry and frame independence. This tension illustrates the ongoing challenge of reconciling intuitive metaphysical views of time with the empirical structure of space-time. From the standpoint of human experience, the growing block universe matches closely with how we perceive time. We feel the present moment as uniquely vivid and real, while the past exists as a fixed record in memory, and the future remains open and uncertain. The theory elegantly mirrors this phenomenology, grounding subjective temporal experience in an objective metaphysical framework. It also supports the common intuition that the past is unchangeable, as it is literally set in stone within the growing block, while the future is genuinely contingent and not yet real. In terms of scientific cosmology, the growing block universe can be related to theories of the expanding universe. Just as space itself is expanding, one might imagine that the block of space-time is similarly growing as new moments are added. This analogy, while not precise, provides a vivid metaphor for how the universe's temporal dimension might develop dynamically. Some physicists and philosophers speculate that a more fundamental theory of quantum gravity might incorporate a version of the growing block idea, where space-time itself is emergent and continually being generated. The growing block also has ramifications for the understanding of death and existence. If the past is fixed and real, then the moments of our life that have passed continue to exist in the block. This has led to philosophical discussions about the persistence of persons after death, whether we continue to exist in the block as past moments or whether existence requires being at the moving present edge. This raises deep questions about identity, consciousness, and what it means to be alive or real. Furthermore, the growing block universe has been linked to the debate over temporal ontology and modal metaphysics. The openness of the future suggests a modal realism of possibilities, where many potential futures exist as mere possibilities, but only one future will be actualized as the block grows. This introduces a subtle interplay between metaphysical possibility and temporal reality, raising questions about how modal facts relate to temporal facts. Critics of the growing block universe point out its difficulties with defining the present moment objectively and its apparent conflict with relativity. Additionally, some argue that it does not fully solve the problem of the flow of time, merely relocating the puzzle to the growing edge of the block. There is also debate about whether the theory can adequately account for the phenomenology of time or whether it is just a metaphysical compromise between opposing views. Despite these challenges, the growing block universe remains a vibrant and influential idea in the philosophy of time. It offers a compelling picture of a temporal reality that is neither wholly static nor entirely fleeting, but a dynamic process of becoming with a fixed past and an open future. This view captures much of our lived experience of time's passage and offers fertile ground for further exploration in physics, metaphysics, and consciousness studies. Next, we will explore the Wheeler-DeWitt equation, a profound concept from quantum gravity that suggests the universe may be fundamentally timeless at the deepest levels of physical reality, challenging conventional notions of time as a flowing dimension. The Wheeler-DeWitt equation stands as one of the most profound and puzzling insights emerging from the quest to unify quantum mechanics with general relativity. Developed in the 1960s by physicists John Archibald Wheeler and Bryce DeWitt, this equation is intended to describe the quantum state of the entire universe. What makes it especially striking and relevant to our exploration of whether time is an illusion is that it contains no explicit time variable. This absence of time in the equation implies that at the most fundamental level of physics, the universe might be timeless, a radical departure from our everyday experience and classical physics treatment of time as a continuous flowing parameter. The Wheeler-DeWitt equation arises from applying the principles of quantum mechanics to the geometry of space-time itself. In classical general relativity, space-time is dynamic, curved by matter and energy, and evolving in time. But when physicists attempt to describe this evolving geometry quantum mechanically, they arrive at a wave function that encapsulates all possible configurations of the universe's geometry. The Wheeler-DeWitt equation governs this wave function. Unlike the Schrödinger equation in non-relativistic quantum mechanics, which explicitly involves time to describe how a system evolves, the Wheeler-DeWitt equation is a timeless equation. It is essentially a constraint equation that sets the wave function's allowed states, but does not specify how it changes in time, because there is no time variable. This timelessness is often called the problem of time in quantum gravity. It challenges the foundational assumption that time is a fundamental parameter according to which physical systems evolve. Instead, the Wheeler-DeWitt framework suggests that time, as we know it, might be emergent rather than fundamental, arising only when we consider subsystems within the universe or particular observers who experience change and sequencing. The universe's wave function itself exists in a timeless, all-encompassing quantum state. This perspective overturns the classical view of time as a universal, flowing dimension and replaces it with a more abstract, holistic conception. Understanding this equation requires grappling with the nature of the wave function of the universe, a concept that defies straightforward physical interpretation. Unlike ordinary wave functions in quantum mechanics, which describe probabilities of finding particles in certain positions or states at given times, the wave function of the universe describes the probabilities for the geometry and contents of the entire cosmos in all possible configurations. The Wheeler-DeWitt equation encodes this state without reference to time, indicating that all moments are encapsulated timelessly within this cosmic quantum description. One way physicists try to reconcile this timelessness with our experience of time's flow is to invoke the concept of emergent time. This idea posits that time arises from correlations between subsystems or internal clocks within a universe. For example, if you consider one part of the universe as a clock and another part as a system being measured, the relative changes between these parts can create an effective sense of time passing. Time then becomes an approximate, relational parameter, not a fundamental dimension. The Wheeler-DeWitt equation, with its timeless wave function, provides the backdrop against which these emergent times can be defined. Another critical aspect is that the Wheeler-DeWitt equation often emerges in approaches to quantum gravity, the theoretical framework that aims to reconcile the principles of quantum mechanics with Einstein's theory of general relativity. Quantum gravity is essential because the classical notion of space-time breaks down at extremely small scales, such as near black holes or the Big Bang. The timelessness implied by the Wheeler-DeWitt equation reflects this breakdown. At the quantum level of space-time itself, the classical concept of a smooth, continuous time dimension might no longer apply. This notion challenges our very intuition about reality. If the fundamental fabric of the universe is timeless, then what we perceive as time's flow may be a derived or effective phenomenon, akin to a movie projection giving an illusion of motion from a sequence of still frames. The Wheeler-DeWitt equation represents a mathematical manifestation of this idea, where the movie is encoded timelessly in the wave function, and time emerges only through the relational structure of its components. The implications extend deeply into philosophical questions as well. If the universe is fundamentally timeless, then notions of causality, change, and becoming need rethinking. Causality, typically understood as a temporal relation where causes precede effects, may need reformulation in a framework where the fundamental description of reality lacks time altogether. Some philosophers and physicists propose that causality might be an emergent, approximate notion, valid only within the effective time experienced by observers. Moreover, the Wheeler-DeWitt equation's timelessness resonates with certain metaphysical positions like eternalism, where all moments of time, past, present, and future, are equally real and fixed in a four-dimensional space-time block. However, the Wheeler-DeWitt approach adds a quantum twist. The block itself is described not by fixed events, but by a quantum superposition of all possible geometries and matter configurations. Reality at its deepest level might then be a timeless quantum entity, a vast, static wave function embodying every possibility. The timeless Wheeler-DeWitt framework also opens intriguing avenues for understanding the origins of the universe. If time is not fundamental, then asking what happened before the Big Bang may be a misguided question, as the classical notion of before requires a temporal framework that does not exist at the quantum gravitational level. Instead, the universe's wave function described by the Wheeler-DeWitt equation includes the entirety of its history in a timeless way, sidestepping paradoxes that arise from temporal beginnings. Scientists and philosophers are still actively debating how to interpret and apply the Wheeler-DeWitt equation. Various approaches attempt to recover a notion of time from it, such as the Page-Wooters mechanism, which proposes that time can be understood as correlations within a stationary quantum state. Others explore the role of decoherence, where interactions with an environment cause quantum states to appear classical and temporally ordered. These investigations aim to bridge the gap between the timeless fundamental description and the rich, dynamic temporal experience of everyday life. The Wheeler-DeWitt equation also serves as a reminder of the limits of human intuition when confronting the universe's deepest structures. Our cognitive apparatus evolved to navigate a world where time seems to flow steadily forward, but the fundamental laws governing the cosmos may defy this familiar experience. The timelessness embedded in the Wheeler-DeWitt equation invites us to rethink not only physics, but also our philosophical understanding of reality, existence, and our place in the universe. In summary, the Wheeler-DeWitt equation profoundly challenges the conventional view of time. It suggests that time may not be a fundamental component of the universe, but rather an emergent property arising from deeper, timeless quantum states. This radical idea reshapes the dialogue between physics and philosophy, urging us to consider a reality where time is not the background against which events unfold, but a derived feature emerging from the timeless quantum fabric of the cosmos. As we continue exploring theories of time, this equation stands as a towering milestone, embodying the mysteries and paradoxes that make the question, could time be an illusion, so compelling. Next, we will delve into the Page-Wooters mechanism, a fascinating approach that attempts to recover the experience of time as an emergent phenomenon from a fundamentally timeless quantum universe, building upon and addressing some of the puzzles raised by the Wheeler-DeWitt equation. The Page-Wooters mechanism offers a captivating and elegant solution to the timelessness problem posed by the Wheeler-DeWitt equation. Developed by Don Page and William Wooters in the early 1980s, this framework reimagines time not as a fundamental background parameter, but as an emergent property that arises from the correlations within a timeless quantum universe. In essence, it suggests that what we perceive as the passage of time is actually a manifestation of entanglement and relational change between parts of the universe. The mechanism offers a way to reconcile a fundamentally timeless global state with the lived experience of a flowing, ordered time by observers embedded within that universe. At the heart of the Page-Wooters mechanism lies the idea that time can be understood relationally rather than absolutely. Instead of the universe evolving in time, the total universal wave function remains static, an unchanging quantum state that encodes all possible configurations. Within this state, however, subsystems become entangled in such a way that one subsystem can serve as a clock for the others. By conditioning on the state of this internal clock subsystem, an effective notion of time emerges for the remainder of the universe. This relational view draws heavily from the concept of quantum entanglement, where parts of a system are interconnected so deeply that the state of one part instantaneously influences the state of another, regardless of distance. Imagine, for example, a simple two-part quantum system where one subsystem acts as a clock. The overall state is static, not changing with respect to any external time parameter. But if we look only at one subsystem, say, the universe minus the clock, its state appears to evolve relative to the state of the clock subsystem. Observers inside the universe, who are themselves part of these subsystems, perceive this evolution as the passage of time. This relational time is not fundamental. It is emergent from the entanglement structure of the universal quantum state. Time, in this view, is essentially the unfolding of correlations between different parts of the universe. This approach has profound implications for our understanding of reality. It challenges the classical notion of a universal, absolute time ticking independently outside the universe. Instead, time becomes a contextual, observer-dependent phenomenon, arising only when an internal clock subsystem exists to serve as a reference. Without such a subsystem, The universe's state remains timeless and unchanging. The Page-Wooters mechanism thereby dissolves the paradox of a timeless wave function and a flowing experience of time by embedding time within the quantum correlations themselves. One of the key strengths of this mechanism is that it respects the principles of both quantum mechanics and general relativity. It starts with a timeless universal quantum state, consistent with the Wheeler-DeWitt equation, and recovers the appearance of time and dynamics without introducing an external time parameter. This aligns with the idea that time, as seen in general relativity, is not absolute, but rather relative and intertwined with space and matter. In a quantum cosmological setting, the Page-Wooters approach provides a framework where time and dynamics emerge naturally from quantum entanglement patterns. The philosophical ramifications of the Page-Wooters mechanism are equally profound. It supports a relational ontology, where the fundamental reality consists of correlations between systems rather than absolute states evolving in an external time. This is a shift from a Newtonian view of time as a universal backdrop to a Leibnizian relational perspective, where time exists only insofar as relationships and changes among entities are defined. It also resonates with some interpretations of quantum mechanics, such as the relational interpretation, which posits that the properties of quantum systems, including time, only have meaning relative to other systems. Experimentally, the Page-Wooters mechanism has inspired physicists to test its predictions and implications. Some quantum experiments simulate entangled systems that behave like internal clocks, demonstrating that relative evolution can be observed in a globally static quantum state. Although testing the full cosmological application remains beyond current capabilities, these experiments provide encouraging support for the mechanism's conceptual foundation. Additionally, this framework prompts a re-evaluation of the nature of time in quantum gravity research. If time arises from entanglement within a timeless state, then understanding the structure and dynamics of entanglement in the universe could be the key to understanding the emergence of time itself. This connects deeply with ongoing studies in quantum information theory, where entanglement is recognized as a fundamental resource and structural component of quantum systems. The Page-Wooters mechanism also elegantly addresses the so-called problem of time in quantum gravity, which stems from the fact that canonical quantum gravity formulations like the Wheeler-DeWitt equation lack a time parameter. By showing that an effective time parameter can emerge from entanglement correlations, it provides a conceptual resolution without requiring any modifications to the fundamental timeless quantum framework. Moreover, the mechanism implies that observers inside the universe will inevitably experience a flow of time, even if the universe's overall state is timeless. This experiential time emerges naturally as a consequence of how quantum correlations structure the universe's state, reinforcing the idea that our subjective experience of time is consistent with a fundamentally timeless reality. In this sense, the Page-Wooters mechanism offers a bridge between the mathematical formalism of timeless quantum cosmology and the phenomenology of time as lived and measured. It reframes time not as a primitive dimension or flow, but as an emergent, relational property, something that exists because parts of the universe are intertwined in complex quantum ways. The mechanism also fits within broader attempts to understand how classical reality, including the flow of time, arises from quantum foundations. It suggests that time is not a backdrop against which events unfold, but an emergent feature of the web of quantum relationships. This perspective encourages a more holistic and interconnected understanding of physical reality, where time, space, and matter emerge together from deeper quantum principles. In the grander scheme, the Page-Wooters mechanism emphasizes that time's illusionary character is deeply rooted in the structure of quantum mechanics itself. While we experience time as a continuous progression, at the fundamental level, it is better understood as a derived concept arising from entangled relationships within a static quantum universe. As we contemplate the nature of time through the lens of the Page-Wooters mechanism, we are invited to consider that our perception of time's passage is not a direct reflection of the universe's fundamental structure, but rather an emergent phenomenon born of quantum entanglement and relational dynamics. This viewpoint has transformative potential for physics and philosophy, reshaping how we conceptualize reality, causality, and existence. Next, we will explore loop quantum gravity, a leading approach in quantum gravity research that offers insights into the discrete structure of space-time and the nature of time at the Planck scale, further expanding our understanding of whether time is fundamental or an emergent illusion. Loop quantum gravity, LQG, presents one of the most compelling and mathematically rigorous approaches to understanding the quantum nature of space-time. Unlike classical general relativity, which models space-time as a smooth and continuous fabric, LQG proposes that at the smallest scales, the Planck scale, around 10 to the power of negative 35 meters, space and time themselves are quantized, made up of discrete, indivisible units. This radical shift challenges our traditional understanding of time as a continuous flowing river and instead suggests that time, much like space, might be composed of tiny, granular chunks or quanta, fundamentally changing how we perceive its nature. The core idea of LQG is that space-time is not a continuous manifold, but rather a network of finite loops called spin networks. These loops form a web-like structure that represents the quantum states of the gravitational field. As these spin networks evolve, they produce spin foams, which represent the quantum history of space-time. These spin networks and spin foams are inherently discrete, implying that space itself consists of minimal units, and by extension, time, which is intertwined with space in the fabric of space-time, may also be fundamentally discrete or even emergent from these quantum structures. One of the revolutionary implications of LQG is that the classical concept of a smooth timeline breaks down at the Planck scale. If space-time is granular, then the notion of continuous time progression ceases to apply at that scale. Instead, what we experience as time's flow might emerge from the complex interplay of these discrete quantum geometries. This raises the possibility that time, as a fundamental entity, might not exist at all. Rather, it could be an emergent phenomenon, appearing only at larger scales where the granular quantum structure smooths out to produce the continuum we observe in everyday life. Moreover, LQG offers a potential solution to some of the paradoxes that arise when trying to merge quantum mechanics and general relativity. For instance, classical general relativity predicts singularities, points where the curvature of space-time becomes infinite, such as the center of black holes or the Big Bang. In LQG, the discrete nature of space-time prevents these singularities by imposing a smallest possible unit of volume, length, and time. This means that space-time cannot be infinitely compressed, fundamentally altering the dynamics of gravitational collapse and the origins of the universe. Time, as we understand it, may cease to have meaning inside such quantum gravitational regimes. This theory also interacts intriguingly with the concept of the Wheeler-DeWitt equation's timelessness. In LQG, the quantum state of the universe is described without a fundamental time parameter, echoing the timeless nature of the Wheeler-DeWitt formalism. Instead, time might emerge from the relational changes of these quantum loops, similar in spirit to the Page-Wooters mechanism, but embedded in a framework that gives precise quantum geometrical meaning to space and potentially time as well. LQG's discrete space-time picture also challenges the notion of causality at the smallest scales. If time is quantized or emergent, then causal order, traditionally based on continuous time, must be reinterpreted. The evolution of spin networks and spin foams suggests a kind of quantum causal set, where causality emerges from the combinatorial relationships between quantum events. This leads to novel approaches like causal set theory, which we will explore later, but it is within LQG that the notion that time may not exist fundamentally first takes a precise mathematical form. From a philosophical perspective, loop quantum gravity challenges the deeply rooted intuition of time as a universal, ever-flowing backdrop. It suggests instead that our classical experience of time is a macroscopic illusion, arising from the collective behavior of microscopic quantum events. This resonates with ideas of time as a human construct or emergent property, but grounds these concepts in a rigorous physical theory, giving them real predictive power and mathematical robustness. In addition to these theoretical insights, LQG has led to interesting predictions and avenues for experimental tests. While probing Planck-scale physics remains far beyond current technology, indirect tests are conceivable, such as examining how space-time discreteness might affect the propagation of high-energy cosmic rays or the polarization of light from distant astrophysical sources. These potential tests could reveal subtle quantum fuzziness of space-time, providing empirical clues about the fundamental nature of time. One of the most exciting applications of LQG is in cosmology, specifically in the study of the early universe and black holes. Loop quantum cosmology, a branch of LQG, replaces the classical Big Bang singularity with a big bounce, where the universe contracts to a minimum volume before expanding again. Here, the classical notion of time breaks down near the bounce, and the quantum gravitational effects dominate. The temporal ordering of events near this bounce challenges conventional time concepts, supporting the idea that time might emerge only after the universe transitions through this quantum gravitational phase. Furthermore, LQG provides a framework where the problem of time and quantum gravity can be addressed more coherently. It suggests that time is not an external parameter, but must be reconstructed from within the theory itself, based on internal relational dynamics of quantum geometry. This reconstruction aligns with various philosophical positions like relationalism, where time exists only through relations among physical events and systems, rather than as an independent entity. The mathematical structure of LQG also offers intriguing links to other theories and ideas discussed in modern physics. For example, its discrete spin networks have analogies with the holographic principle and the idea of the universe as a vast informational or computational structure, connecting to theories like digital physics and the simulation hypothesis. These connections highlight a growing trend in physics toward understanding reality as fundamentally informational or computational, where time might be a processing sequence or emergent parameter rather than a fundamental dimension. At the conceptual level, LQG invites us to reconsider the role of time in consciousness and experience. If time is not fundamental but arises from quantum geometry, how does this influence our perception of time? Neuroscientific research already points to the brain's interpretation of time as a construct, subject to delays and illusions. If our brain's timekeeping depends on physical processes grounded in an emergent temporal dimension, it suggests that human temporal experience is deeply tied to these quantum geometric structures. Loop quantum gravity's discrete spacetime also suggests that continuous symmetries, fundamental to many physical laws, may be approximate at the Planck scale. This could mean that time reversal symmetry, thermodynamic arrow of time, and other temporal asymmetries are emergent phenomena, not fundamental laws. The direction and flow of time may arise from statistical or thermodynamic behavior on a background of fundamentally timeless quantum geometry. Overall, loop quantum gravity paints a picture of a universe where time, as classically conceived, does not exist at the most fundamental level. Instead, what we call time may be a macroscopic illusion, an emergent property arising from the dynamics of discrete quantum spacetime. This revolutionary insight pushes the boundaries of physics and philosophy alike, encouraging new ways of thinking about existence, causality, and the flow of reality. As we continue, we will explore time dilation, a phenomenon predicted by Einstein's theory of relativity, which demonstrates that time is not absolute, but can stretch and contract depending on speed and gravity. This phenomenon further complicates the notion of time as a universal constant, introducing relativistic effects that challenge our everyday intuitions about time's passage. Time dilation is one of the most striking and experimentally verified consequences of Einstein's theory of relativity. It fundamentally challenges the notion of absolute, universal time that ticks identically for every observer regardless of their state of motion or location. Instead, time dilation reveals that time itself is relative. It can stretch or compress depending on how fast you're moving or how strong the gravitational field you're in. This phenomenon not only alters our understanding of time's nature, but also raises profound questions about whether time itself exists as a universal flow or is instead a flexible, observer-dependent experience. To begin, special relativity introduced the idea that the laws of physics are the same for all observers moving at constant velocities, and that the speed of light is a universal constant, regardless of the motion of the source or observer. From these postulates arises the conclusion that measurements of space and time are relative, depending on the observer's frame of reference. A particularly startling result is time dilation, where a moving clock is observed to tick more slowly compared to a stationary clock from the perspective of the stationary observer. This effect isn't merely a theoretical prediction. It has been confirmed repeatedly through experiments involving precise atomic clocks on fast-moving airplanes and satellites. Time dilation due to velocity is explained by the Lorentz transformations, which mathematically describe how space and time coordinates change for observers moving relative to each other. As an object approaches the speed of light, its time relative to an outside observer slows dramatically. From the viewpoint of someone traveling at near light speed, their own clock runs normally, but an outside observer sees their clock running slow. This means that two observers moving relative to each other do not agree on how much time has passed between two events, underscoring that time is not absolute, but deeply linked to motion. General relativity extends these insights to include gravity, which is understood not as a force, but as a curvature of space-time caused by mass and energy. In this framework, the presence of a massive body warps the fabric of space-time, causing clocks closer to the mass to tick more slowly relative to clocks farther away. This gravitational time dilation has also been experimentally confirmed, for example, by comparing atomic clocks at different altitudes, where clocks at higher elevations, experiencing weaker gravity, run faster than those at sea level. The practical implications are immense. Global positioning systems, GPS, must account for gravitational time dilation to provide accurate location data. This relativistic behavior dismantles the classical notion of a universal present moment. If two observers in different gravitational potentials or moving at different velocities cannot agree on simultaneous events, then the idea of a universal now collapses. Each observer has their own subjective present, their own slice of space-time, and time becomes a deeply personal dimension rather than a shared constant. This undermines our intuitive experience of time as a steady and universal flow and opens the door to interpreting time more flexibly and relationally. Time dilation also brings profound philosophical implications. If time can slow or speed up depending on the observer's frame, then time itself cannot be a fundamental, absolute feature of reality. Instead, it must be understood as a relational quantity, depending on context and perspective. This ties into ideas like the block universe theory, where all events, past, present, and future, exist equally in a four-dimensional space-time manifold, and our perception of time's passage is merely our movement along this dimension. Time dilation thus acts as strong empirical support for models of time, where the flow or passage is an emergent or subjective phenomenon. Moreover, time dilation confronts us with intriguing scenarios such as the famous twin paradox, where a twin traveling near light speed ages more slowly than their sibling who remains on Earth. Upon returning, the traveling twin is biologically younger, despite both having lived through what they consider their own proper time. This paradox, resolved within relativity, vividly illustrates how time intervals depend on an observer's trajectory through space-time, not just on a universal clock. It reinforces the idea that time is a personal and path-dependent quantity, not a universal absolute. In terms of cosmology, time dilation affects how we observe distant astrophysical phenomena. Light from rapidly moving objects such as jets emitted by black holes or neutron stars is stretched, and the timing of signals we receive is altered by gravitational fields. This impacts how we measure and understand cosmic history, indicating that our observations of the universe's past are filtered through layers of relativistic time effects. Even at the quantum scale, time dilation remains relevant when considering how fundamental particles experience time in extreme environments or high-energy collisions. Particle lifetimes, such as those of muons created in the atmosphere by cosmic rays, are extended when observed from Earth because these particles move at relativistic speeds, surviving longer than expected in their rest frame. This phenomenon is a clear and direct manifestation of time dilation, bridging the gap between the quantum and relativistic worlds. Time dilation also interfaces with other theories that question the fundamental nature of time. For example, it aligns with the idea of emergent time, because the variability of time flow suggests it cannot be fundamental but must arise from deeper principles, be they geometric, informational, or quantum mechanical. The non-absolute nature of time introduced by relativity provides a necessary backdrop for quantum gravity theories like loop quantum gravity and the Wheeler-DeWitt equation, which envision a timeless foundation beneath apparent temporal flow. Furthermore, time dilation has technological and practical consequences that influence our daily lives in subtle but critical ways. The synchronization of atomic clocks in the global navigation satellite systems must constantly adjust for the relativistic effects of both velocity and gravity. Without accounting for time dilation, GPS devices would quickly become inaccurate, drifting kilometers off target within hours. This practical reality firmly grounds the abstract concept of time dilation in everyday experience. Interestingly, time dilation also opens the door to speculative but scientifically grounded ideas like time travel to the future. Since moving at near-light speeds slows time relative to an outside observer, one could theoretically travel into the future faster than normal aging would allow, arriving at a future moment while having experienced less time themselves. Although currently beyond our technological reach, this possibility highlights how time dilation blurs the boundaries between science fiction and physical reality. From a human perspective, time dilation challenges our intuitive experience of simultaneity and duration, prompting reflection on how our brains perceive and measure time internally. Just as the external universe exhibits time dilation, so might our neurological processes introduce distortions or relativistic-like effects on a psychological timescale. This suggests fascinating intersections between physics, neuroscience, and philosophy in understanding how time is experienced versus how it physically unfolds. In sum, time dilation demonstrates that time is not a fixed and absolute parameter, but a flexible dimension, deeply intertwined with space, motion, and gravity. It underscores the relativity of time, highlighting that temporal intervals depend on the observer's frame of reference. This revelation reshapes our understanding of time from a universal flow into a complex, observer-dependent phenomenon, providing critical empirical support to many of the philosophical and physical theories that question the fundamental existence of time itself. As we continue, we will explore retrocausality, a concept in quantum physics suggesting that effects can precede their causes, further complicating our notions of temporal order and causality in a universe where time may not flow in the familiar forward direction. Retrocausality presents a radical challenge to the conventional understanding of time, causality, and the very sequence of events. Traditionally, cause and effect are perceived to follow a strict temporal order. Causes precede effects, and the future is shaped by the past, never the other way around. This one-way flow underpins much of classical physics, everyday reasoning, and our subjective experience of time. However, retrocausality turns this notion on its head by proposing that, at least on the quantum level, future events can influence past events, suggesting a breakdown of the familiar arrow of time and a more complex temporal relationship than we typically imagine. At its core, retrocausality posits that the causal influence is not strictly forward-moving, but can flow backward in time as well. This idea has gained traction primarily from interpretations of quantum mechanics, particularly those attempting to explain puzzling phenomena like quantum entanglement and the measurement problem without violating locality or realism. One of the key motivations behind retrocausal interpretations is to reconcile the strange instantaneous correlations seen in entangled particles with the principle that no information can travel faster than light, as demanded by relativity. By allowing the future measurement settings to affect past particle states, retrocausality provides a framework that preserves locality but sacrifices the classical notion of temporal causality. The concept can be illustrated through variations of the famous delayed choice experiments first proposed by physicist John Wheeler. In these experiments, the decision of what measurement to perform on a photon is made after the photon has entered an apparatus. Yet the results suggest that the photon's earlier behavior is influenced retroactively by this later choice. This seems to imply that the future measurement retroactively determines the past state of the photon. While interpretations vary, retrocausality offers a way to make sense of this by allowing backward-in-time influences, effectively blending past and future in a non-classical causal web. Retrocausality also challenges the standard thermodynamic arrow of time, which is based on the increase of entropy and underlies the irreversibility of macroscopic processes. While entropy increases over time, giving a clear direction to time's flow, retrocausal effects suggest that, at fundamental levels, temporal order may be symmetric or even bidirectional. This discrepancy between micro-level temporal symmetry and macro-level asymmetry is one of the great puzzles in physics, and retrocausality nudges us to reconsider whether the apparent arrow of time is a mere emergent phenomenon rather than a fundamental property. From a philosophical standpoint, retrocausality questions the linear narrative of cause and effect that undergirds much of human understanding. If the future can influence the past, the distinction between what is determined and what is free becomes murky. Concepts such as free will, determinism, and the openness of the future come under scrutiny as the classical sequence of events no longer holds universally. This also poses problems for notions of responsibility and decision-making, which depend on a clear temporal order. Retrocausality also intersects intriguingly with the block universe theory. If all points in time, past, present, and future, are equally real and fixed within a four-dimensional space-time manifold, then causal influences traveling backward in time might be less paradoxical than they seem. In such a universe, time's flow is an illusion, and retrocausality becomes a natural consequence of the timeless block, where temporal relations are more about spatial geometry than a strict before and after ordering. In the realm of quantum foundations, retrocausal models attempt to provide an elegant explanation for the puzzling non-local correlations observed in experiments violating Bell's inequalities. By allowing backward causation, these models retain locality, the principle that objects are only directly influenced by their immediate surroundings, while explaining correlations that otherwise appear instantaneous and spooky. This helps reconcile quantum mechanics with relativity, a long-standing challenge in physics. However, retrocausality is not without its critics. Many physicists argue that retrocausal interpretations introduce more conceptual difficulties than they solve, risking logical paradoxes, such as causal loops or violations of causality that would allow for time travel paradoxes. Moreover, there is no consensus on how to experimentally distinguish retrocausal effects from other interpretations of quantum mechanics, such as the many worlds or Copenhagen interpretations. Despite these challenges, retrocausality inspires new theoretical frameworks and experiments. Some proposals involve looking for subtle temporal correlations that might indicate backward causation, or to devising new quantum information protocols that exploit retrocausal influences. Such research pushes the boundaries of our understanding of time, causality, and reality itself. On a metaphysical level, embracing retrocausality forces us to rethink the nature of time itself. Instead of viewing time as a river flowing from past to future, it becomes a more complex structure where past, present, and future are intertwined in a dynamic, non-linear tapestry. This resonates with other timeless or block universe perspectives, suggesting that our conventional experience of time is a limited slice of a far richer temporal landscape. Furthermore, retrocausality dovetails with ideas from information theory and the holographic principle, where information encoded on a boundary or horizon can influence the bulk space-time in non-intuitive ways, potentially including influences that cross temporal boundaries. This hints at a deeper informational substrate of reality where causal relations transcend classical temporal order. Retrocausality also raises profound questions about consciousness and perception. If the future can influence the past, might our experience of decision-making or memory be affected by events that have not yet happened? While speculative, this idea invites interdisciplinary exploration, bridging physics, neuroscience, and philosophy of mind to investigate how temporal cognition might reflect or conceal these deeper temporal symmetries. The interplay of retrocausality with other time theories is rich and complex. For example, in the context of the Wheeler-DeWitt equation, which lacks explicit time dependence, retrocausality might offer a way to understand how temporal order emerges or is encoded in a fundamentally timeless quantum gravitational framework. Similarly, the Page-Wooters mechanism, which derives time from quantum entanglement within a timeless universe, might be compatible with or enhanced by retrocausal influences. In sum, retrocausality challenges the bedrock assumptions of temporal order and causality by suggesting that the future can affect the past. While still a controversial and speculative idea, it offers compelling explanations for quantum phenomena that defy classical logic and pushes the boundaries of how we understand time's nature. By destabilizing the arrow of time, retrocausality invites us to reconsider time not as a simple linear sequence, but as a complex, interconnected web of temporal relations, fundamentally altering our grasp of reality. Next, we will delve into thermodynamic time, exploring how the second law of thermodynamics introduces an arrow to time through entropy increase, and how this shapes our perception of temporal flow and irreversibility. Thermodynamic time introduces one of the most intuitive and empirically grounded explanations for why we experience time as flowing in one direction. The arrow of time arises because of entropy, the measure of disorder or randomness in a system. This perspective is rooted in the second law of thermodynamics, which states that in an isolated system, entropy tends to increase over time. Unlike many physical laws, which are time-symmetric and apply equally forward and backward in time, the second law gives us a fundamental asymmetry, a directionality that is unique to the macroscopic world and underpins why we remember the past, but not the future, why cause precedes effect, and why certain processes are irreversible. The concept of entropy was first formalized in the 19th century, primarily through the work of Rudolf Clausius and Ludwig Boltzmann. It emerged as a statistical measure of the number of microscopic configurations consistent with a system's macroscopic state. A highly ordered system, like a neatly arranged deck of cards, has low entropy because it represents only a few possible configurations. Conversely, a shuffled deck has high entropy, representing countless configurations. Over time, natural processes tend to move from low entropy to high entropy states because high entropy states are vastly more probable, statistically speaking. When applied to the entire universe, thermodynamic time suggests that the flow we experience is not an intrinsic feature of time itself, but a reflection of this ever-increasing disorder. The past corresponds to lower entropy conditions, such as the highly ordered early universe shortly after the Big Bang, while the future represents a state of higher entropy, where systems become increasingly disordered. This perspective shifts the focus away from time as a fundamental dimension or a flowing river, emphasizing instead how the changing arrangements of matter and energy give rise to our temporal experience. This entropic arrow of time elegantly explains why certain processes are irreversible. For instance, we can break an egg, but we never see the shattered pieces spontaneously reassemble into a perfect egg. This irreversibility arises because the forward direction leads to a more probable high entropy state. while the reverse process would require an extraordinary decrease in entropy, something so statistically improbable it effectively never happens. This asymmetry, tied to entropy, is deeply embedded in everyday life and all macroscopic phenomena. However, when we look deeper into the fundamental laws of physics, the picture becomes more complicated. The microscopic laws governing particles, such as those in quantum mechanics and classical mechanics, are largely time-symmetric, meaning they do not inherently distinguish between past and future. This discrepancy between microscopic time symmetry and macroscopic time asymmetry is known as the problem of the arrow of time, and remains one of the central puzzles in theoretical physics. Boltzmann himself proposed a statistical explanation, suggesting that entropy increases because of overwhelmingly probable statistical distributions. But this explanation assumes a very special low-entropy initial condition of the universe. Why the universe began in such an improbably low-entropy state remains a profound mystery and ties thermodynamic time to cosmology and the origins of the universe. The concept of thermodynamic time also has implications for how we perceive causality and memory. Our brains, as physical systems, rely on processes that increase entropy, creating memories by establishing stable patterns of neural connections. These processes are themselves irreversible and tied to the thermodynamic arrow of time. Thus, the directionality of time in our conscious experience is intimately linked to the thermodynamic processes occurring within our bodies and the environment. This arrow also aligns with the notion of time's passage as an emergent phenomenon rather than a fundamental aspect of reality. If time's directionality depends on the statistical behavior of complex systems and their entropy, then on a fundamental level, time might not have a preferred direction at all. Instead, time's flow could emerge from the collective behavior of countless particles and interactions. Furthermore, thermodynamic time bridges physics and philosophy by challenging our assumptions about the nature of reality. It raises questions about determinism and the possibility of time travel, since reversing time's arrow would require entropy to decrease, a scenario not supported by any known natural process. On the cosmological scale, thermodynamic time connects with theories about the ultimate fate of the universe. As entropy increases, the universe may approach a state of maximum entropy known as heat death, where no usable energy remains to fuel processes, and time, as we understand it, effectively ceases to have meaning in a thermodynamic sense. This ties thermodynamic time closely to existential and philosophical questions about the meaning and temporality of existence. Interestingly, thermodynamic time contrasts sharply with some other theories like Presentism or the block universe. While those suggest that time is either an illusion or a fixed dimension, thermodynamic time focuses on change and irreversibility, dynamic aspects tied to physical processes rather than abstract metaphysical constructs. Thermodynamic time also complements other ideas, such as emergent time, suggesting that what we perceive as time arises from the complex interplay of fundamental timeless laws and the statistical behavior of large systems. It offers a pathway from the timeless microphysics to the temporal macro world we inhabit. Despite its explanatory power, thermodynamic time is still subject to debate and open questions. Some physicists ask whether entropy really increases everywhere or if there might be regions or conditions where it decreases. Others explore the links between entropy and information theory, considering whether the flow of time is tied to the processing and loss of information in physical systems. Moreover, the relationship between thermodynamic time and quantum mechanics remains an active area of research. Quantum decoherence, the process by which quantum systems interact with their environment and lose coherent properties, is closely related to entropy increase and helps explain why the classical world emerges from quantum uncertainty with a clear arrow of time. In sum, thermodynamic time offers a powerful and compelling explanation for the arrow of time as an emergent property of entropy increase. It aligns well with everyday experience, provides deep links between physics and consciousness, and frames time's flow as a statistical macroscopic phenomenon rather than a fundamental feature of the universe. This perspective continues to influence modern physics, cosmology, and philosophy, fueling ongoing discussions about whether time is truly fundamental or a convenient and emergent construct rooted in the universe's thermodynamic behavior. Next, we will explore the simulation hypothesis, which suggests that our perception of time, and indeed reality itself, could be an artifact of living within a computational simulation, raising profound questions about the nature of time, reality, and consciousness. The simulation hypothesis presents a fascinating and controversial perspective on the nature of reality and time. It posits that our entire universe, including everything we perceive as real, is actually a complex simulation run by an advanced intelligence or civilization. Within this framework, what we experience as time could be nothing more than a programmed variable, a construct embedded in the simulation's code, rather than a fundamental, independent property of the universe itself. The idea of a simulated reality is not entirely new, but it has gained significant traction in both philosophical circles and scientific discourse, particularly due to advancements in computer technology and the growing understanding of computational theory. Proponents argue that if any civilization could reach a level of technological sophistication sufficient to simulate entire universes with conscious beings inside them, then the probability that we ourselves exist in such a simulation could be surprisingly high. If time is a programmed variable within such a simulation, it implies that the flow of time, its direction, speed, and perhaps even its continuity are parameters controlled by the underlying computational framework. This raises questions about whether time could be manipulated, paused, or even rebooted, much like a video game or a digital environment. It suggests that time's apparent consistency and unidirectionality could be artifacts of the programming, designed to maintain the illusion of a coherent and continuous reality for the simulated inhabitants. In this view, the fundamental laws of physics that govern time and space might be reduced to algorithms, rules, or functions written into the code of the simulation. These programmed rules could include the speed of light as a maximum velocity, causality constraints to maintain logical consistency, or even quantum probabilities that mirror the indeterminacy observed in the real world. This aligns with the notion that the universe is governed by information and computation at its core, a concept explored by digital physics and information theory. One of the intriguing aspects of the simulation hypothesis is how it challenges traditional concepts of causality and temporal order. If the simulation's clock or frame rate controls the passage of time, then time could theoretically run at different speeds in different regions or be influenced by processing loads and resource allocation. This idea parallels time dilation effects in relativity, but stems from entirely different principles, namely computational limitations rather than physical laws. Furthermore, the hypothesis opens the door to the possibility that anomalies or paradoxes related to time, such as retrocausality, delayed choice experiments, or even the experience of déjà vu, could be glitches or artifacts within the simulation's code. These bugs might manifest as inconsistencies in the temporal flow or as moments where the usual rules of cause and effect appear to break down, hinting at an underlying artificial structure. Philosophically, the simulation hypothesis raises profound questions about free will, consciousness, and the nature of existence. If time is a programmed variable, then our experience of past, present, and future might be part of an elaborate design to simulate continuity and narrative progression. Consciousness itself could be an emergent property of the simulation's computational processes or might even transcend the simulation, existing independently of the programmed temporal framework. Critics of the simulation hypothesis point out the difficulty of testing or falsifying such a theory, as any evidence within the simulation could itself be part of the programming. However, some scientists and philosophers propose that subtle inconsistencies in the physical constants, unexpected limitations in the universe's resolution, or detectable computational shortcuts might one day reveal clues pointing toward a simulated origin. Additionally, the hypothesis touches on ethical and metaphysical considerations about the simulators themselves, what their purpose might be, whether they observe or interfere with the simulation, and what this means for our understanding of time, morality, and destiny. It also raises the possibility that time as experienced within the simulation is merely a shadow of some higher dimensional or more complex temporal structure in the real universe outside the simulation. From a practical standpoint, the simulation hypothesis encourages a reconsideration of the ontological status of time. Instead of being an absolute entity or a fundamental dimension, time could be a flexible, context-dependent phenomenon shaped by the underlying computational rules. This view resonates with other ideas that see time as emergent or illusory, further blurring the line between physical reality and informational constructs. Moreover, in the context of quantum mechanics and modern physics, the simulation perspective dovetails with interpretations that emphasize information as primary. If the universe is essentially a vast information processing system, then time's flow might correspond to the updating of informational states within the simulation, akin to frames in an animation or clock cycles in a computer processor. The simulation hypothesis also offers an intriguing angle on the nature of temporal paradoxes and phenomena, such as time loops or closed time-like curves predicted in some theoretical physics models. In a simulated reality, such features might be intentionally programmed or result from specific subroutines, potentially explaining why these phenomena have not been observed or are restricted to very specific conditions. In summary, the simulation hypothesis posits a radically different ontological status for time, framing it not as a fundamental dimension or a natural flow, but as a programmed, mutable aspect of a computational reality. This perspective challenges many classical and modern theories of time, urging us to rethink what it means for something to exist in time and whether time itself might be ultimately reducible to informational processes controlled by an external or higher-level system. This hypothesis opens vast conceptual territory, linking physics, philosophy, computer science, and metaphysics, and it remains a stimulating and open-ended field of inquiry. It invites us to consider the possibility that the passage of time, our memories of the past, and even our anticipations of the future could be encoded, simulated experiences designed to create a coherent narrative for conscious entities within an artificial construct. Next, we will explore the ADS/CFT correspondence, a groundbreaking theoretical framework in physics that offers a dual description of the universe, where time might emerge differently in two related but distinct realms, revealing deeper insights into the fabric of reality and the nature of time itself. The ADS/CFT correspondence, often hailed as one of the most profound discoveries in theoretical physics of the last few decades, proposes a fascinating and intricate relationship between two very different types of physical theories. At its core, the correspondence, also called gauge/gravity duality, asserts that a gravitational theory in a higher dimensional space called anti-de Sitter, ADS, space can be exactly equivalent to a quantum field theory without gravity defined on the lower dimensional boundary of that space, known as conformal field theory, CFT. This duality implies a deep and surprising connection between gravity, quantum mechanics, and the geometry of space-time, and it carries significant implications for our understanding of time. One of the most startling aspects of AD/CFT is the idea that the dimension we perceive as time in our universe could emerge from a fundamentally timeless theory existing in fewer dimensions. In the CFT description on the boundary, time as we know it might not even appear as a basic or independent parameter. Instead, what we interpret as temporal evolution in the bulk AD space emerges from correlations and relationships encoded in the timeless, static boundary theory. This correspondence challenges traditional views of time as a universal, fundamental backdrop against which all events occur. Instead, it suggests that time could be an emergent phenomenon, something that arises only when viewed from within the higher dimensional gravitational context. The timeless nature of the boundary theory means that the fundamental description of reality might be static, with no intrinsic flow or progression of time, and that what we experience as time's passage is a kind of holographic illusion created by the way the bulk geometry encodes information from a boundary. The implications of this idea are immense. If time is emergent from a timeless boundary theory, then questions about the beginning or end of time may become meaningless at the most fundamental level. The flow of time, causality, and temporal ordering could all be secondary effects resulting from how the bulk space-time encodes information and geometry. This reframes time not as a basic dimension akin to space, but as a derivative, higher-level construct arising from a more fundamental, timeless substratum. Physically, the ADS/CFT correspondence has been an invaluable tool for studying strongly coupled quantum systems, black holes, and aspects of quantum gravity that were previously inaccessible. By translating problems in the complex gravitational bulk to more tractable quantum field theories on the boundary, physicists have gained insights into the microscopic structure of space-time and the role of information in gravitational phenomena. This also ties into the idea that the universe might be holographic, that all the information contained within a volume of space can be represented on its boundary. In this holographic framework, time's nature is deeply entwined with the encoding and decoding of information across dimensions. It may be that the classical, continuous flow of time that we observe is an emergent effect of the quantum entanglement structure and information flow on the boundary, projecting into a higher dimensional space-time that we interpret as our universe. Moreover, the ADS/CFT duality provides a window into how quantum gravity might resolve some of the long-standing paradoxes involving time, such as those related to black holes and information loss. Since the boundary theory is unitary and does not lose information, time evolution in the bulk must also preserve information, implying that even in regions of extreme gravity where classical intuitions about time break down, a consistent, underlying timeless theory governs reality. Philosophically, this raises profound questions about what it means for time to exist. If the fundamental layer of reality is timeless, then time's reality depends on our perspective within the bulk space-time, an emergent property tied to the observer's position and the information they can access. This resonates with other timeless approaches to physics and aligns with the idea that time might be a kind of internal parameter, a tool we use to organize experiences rather than a universal entity. In the ADS/CFT framework, the universe can be thought of as a kind of cosmic stage where the script of time is written on a boundary that itself knows no time. Our perception of time's flow is akin to watching a shadow play on the walls of a higher dimensional room. The shadows move and change, but the fundamental reality casting those shadows remains still and timeless. This viewpoint also connects to efforts in quantum gravity and string theory to unify the forces of nature and reconcile the apparent contradictions between general relativity and quantum mechanics. If time is emergent, many perplexing puzzles, such as the problem of time in quantum gravity, where standard notions of time break down, might find resolution by recognizing that time is not fundamental but derived from a deeper, static theory. The ADS/CFT correspondence thus offers a compelling example of how time could be an illusion, or at least a secondary phenomenon, dependent on a more primitive and timeless description of the universe. It suggests that our intuitive experience of past, present, and future might be no more fundamental than the projection of a complex mathematical structure onto a screen. This holographic emergence of time invites us to reconsider our assumptions about reality itself. If what we call time arises from a boundary theory that lacks time, then the ultimate nature of existence may be far stranger and less temporal than everyday experience leads us to believe. In this view, time's passage is not written into the fabric of the cosmos, but is an emergent effect created by how the universe encodes information and geometry across dimensions. Next, we will delve into causal set theory, which proposes a discrete, fundamentally ordered structure of events underlying space-time, offering yet another intriguing perspective on time and its possible illusory nature. Causal set theory presents a revolutionary perspective on the nature of space-time, particularly focusing on the idea that at the most fundamental level, the fabric of reality is not continuous but discrete. Unlike the smooth and continuous space-time manifold portrayed by classical general relativity, causal set theory suggests that space-time consists of a collection of elementary events or atoms of space-time, arranged in a specific order dictated by causality. This approach redefines our understanding of time as something that emerges from the network of these causal relations rather than as a flowing continuum. The essence of causal set theory lies in the principle that the order of events, the cause and effect relationship between them, is more fundamental than the geometric properties we usually associate with space-time. Each causal set is a partially ordered set of discrete points where the order represents the causal structure, which events can influence which others. In this framework, the concept of time arises naturally from the partial order of these events. Time is not a continuous parameter ticking along independently, but an emergent property arising from the way these causal elements are arranged and linked. One of the critical insights of causal set theory is that the continuous geometry of space-time, with its smooth curves and surfaces, is a large-scale approximation of a fundamentally discrete structure. At microscopic scales, space-time is granular, built from indivisible building blocks, and the flow of time is nothing but the unfolding or growth of this causal network. The discrete nature of these events removes the necessity of a background time parameter. Instead, time emerges as the order in which events occur and influence one another. This discrete causal structure avoids some of the paradoxes and difficulties associated with continuum theories of space-time, especially in quantum gravity. For instance, the infinities that plague quantum field theories on continuous spacetimes may be avoided because causal set theory inherently imposes a minimal scale, below which no finer subdivision is possible. This minimal length scale, often associated with the Planck length, acts as a natural regulator, potentially offering a path to a finite and consistent theory of quantum gravity. Importantly, causal set theory challenges our classical intuition of time as a smooth river flowing evenly from past to future. Instead, it suggests that the universe is constructed step by step through discrete events, with time emerging as a measure of the causal depth and ordering of these events. This view aligns with the idea that the passage of time is not an external parameter, but a property of the universe's causal architecture. Philosophically, the theory resonates with the idea that what we perceive as continuous temporal flow is a macroscopic illusion, akin to how a movie film appears to move continuously despite being a sequence of individual frames. The unfolding of the causal set resembles a dynamic process where the now is defined by the set of events causally linked at a given stage, and the future corresponds to events that have not yet been added to this causal order. This approach also has profound implications for the nature of causality and determinism. Since the causal set grows by the addition of new events, time's arrow is naturally embedded within the structure. The past consists of events that have already been integrated into the causal set, while the future is open, represented by events not yet realized. This built-in asymmetry addresses the long-standing question of why time appears to flow in one direction, a feature often linked to entropy, but here grounded in the fundamental architecture of space-time itself. Another remarkable feature of causal set theory is its compatibility with Lorentz invariance, a cornerstone of modern physics which states that the laws of physics are the same for all observers regardless of their motion. Even though the underlying causal set is discrete, its structure respects this symmetry, allowing it to reproduce the relativistic behavior of space-time at large scales. Moreover, causal set theory connects intriguingly with other modern ideas about quantum gravity and space-time emergence. It shares conceptual space with approaches like loop quantum gravity and the holographic principle in its quest to replace the classical, continuous notion of space-time with a fundamentally quantum, discrete substratum. It complements these theories by emphasizing causality as the foundational ingredient from which space-time and time itself are constructed. In terms of physical observables, Causal set theory predicts subtle deviations from classical space-time behavior at extremely small scales or high energies. These deviations could manifest in the form of tiny fluctuations or graininess in the structure of space-time, potentially accessible in future high-precision experiments or observations of cosmic phenomena. Detecting such signatures would provide empirical support for the theory and confirm the discrete nature of time and space-time. The implications of causal set theory extend beyond physics into metaphysics and philosophy of time. It supports a dynamic view of reality where the future is genuinely open and not predetermined, contrasting with block universe interpretations that treat past, present, and future as equally real and fixed. This openness gives room for free will and novelty within a physically grounded framework, where the unfolding causal structure continuously creates new realities. Furthermore, the theory elegantly reconciles the subjective experience of time with objective physical reality. Our conscious sense of temporal flow and the distinction between past, present, and future arise naturally from the discrete causal ordering of events. The now is not an illusion, but a real, dynamically growing frontier in the causal set, constantly moving forward as new events come into existence. In summary, causal set theory paints a picture of time that is fundamentally different from classical physics. Time is no longer a smooth dimension ticking away independently of the events it orders. It is an emergent property arising from the discrete, ordered set of causal relations between fundamental spacetime atoms. This profound shift in understanding challenges the notion of time as a universal backdrop and suggests that our familiar temporal experience is a large-scale consequence of a far more fundamental and discrete causal architecture. Next, we will explore Feynman's path integral formulation, which provides another fascinating lens on time, where the future and past contribute to the present in a sum-over histories approach, challenging the classical notion of a single, fixed timeline. Feynman's path integral formulation revolutionizes the way we understand the quantum behavior of particles and, by extension, time itself. Traditionally, physics treats time as a straightforward parameter along which events unfold in a single, well-defined trajectory. However, Richard Feynman's approach fundamentally challenges this perspective by suggesting that, at the quantum level, particles don't simply follow one path through space-time. Instead, they simultaneously explore every possible path, and the observed behavior emerges from a complex sum over all these histories. This idea profoundly alters our grasp of time, casting doubt on the notion of a singular, continuous flow. The path integral formulation operates by considering a particle traveling from one point to another in spacetime. Instead of assuming it moves along one unique trajectory, Feynman proposed that the particle takes every conceivable path, no matter how wild, looping, or indirect, at once. Each path contributes to the particle's overall behavior through a complex probability amplitude. These amplitudes, when summed, interfere constructively or destructively, resulting in the quantum outcomes we observe. Time, in this framework, is not a linear sequence, but a vast landscape of overlapping histories. This multiplicity of paths implies that the concept of a single now or a fixed temporal sequence is insufficient to capture the quantum reality. Rather than time flowing uniformly and unambiguously, the present moment arises from an amalgamation of many possible pasts and futures. In other words, all potential timelines coexist in a superposition, and the classical idea of time as a straightforward, irreversible arrow is replaced by a tapestry of concurrent possibilities. This leads to an understanding of time that is profoundly non-classical, a network of probabilities and amplitudes instead of a single, concrete thread. Crucially, the path integral method provides a mathematical tool that aligns beautifully with the experimental realities of quantum mechanics. For example, phenomena like quantum interference, tunneling, and superposition find a natural explanation when we acknowledge that particles effectively sample multiple timelines simultaneously. This reinforces the idea that time is not a simple parameter marching forward, but a dimension richly intertwined with the probabilistic nature of quantum events. From a philosophical standpoint, Feynman's formulation invites us to reconsider what it means for events to happen in time. If all possible paths exist, then the past and future are not fixed but fluid, embedded in a grand superposition. The future is not predetermined, but consists of countless potential outcomes, each contributing to the present state. This perspective undermines classical determinism and the intuitive flow of time as an inevitable march from cause to effect. Moreover, the path integral framework has implications for the notion of causality. In classical physics, causes precede effects in a strict temporal order, but the coexistence of multiple histories complicates this straightforward causal chain. Since all possible paths contribute to the observed reality, the boundaries between cause and effect become blurred, hinting at a deeper layer of temporal structure where cause and effect may be intertwined across different histories. This concept also resonates with quantum experiments that challenge classical intuitions, such as the delayed choice and quantum eraser experiments. These experiments suggest that choices made in the present can influence the apparent history of a quantum system, echoing the path integral suggestion that multiple timelines exist simultaneously and that the notion of a single, fixed past is not fundamental. Feynman's path integral formulation also has far-reaching consequences for the search for a quantum theory of gravity. By applying the sum-over-histories approach to space-time itself, physicists attempt to reconcile the principles of quantum mechanics with general relativity. In this context, space-time geometry is not fixed, but emerges from a quantum superposition of all possible geometries and causal structures. This idea dovetails with the notion that time and space are emergent rather than fundamental phenomena. One of the most striking implications of this approach is the way it naturally accommodates the concept of time symmetry. Unlike classical physics, which is heavily time asymmetric due to the thermodynamic arrow of time, quantum mechanics, and particularly the path integral method, treats forward and backward time directions on an equal footing. This symmetry challenges our everyday experience of irreversible time and hints at a universe where time's directionality emerges only under specific macroscopic conditions. The path integral's view of time also challenges our understanding of a universe's origin. If all possible histories coexist, then the Big Bang might not be a single, absolute beginning, but one among countless quantum histories. This opens the door to a multiverse interpretation where different branches of reality unfold from a shared quantum substrate, each with its own temporal structure. Additionally, this approach underscores the role of the observer in defining reality. Since the observed outcome results from the interference of multiple paths, what we perceive as reality is shaped by how measurements collapse this superposition into a single history. This reinforces the idea that time, and indeed reality itself, is deeply connected to observation and information, rather than existing independently as an objective entity. Furthermore, Feynman's formulation has inspired numerous theoretical developments beyond traditional quantum mechanics. It has been instrumental in quantum field theory, string theory, and attempts to unify the forces of nature. In each of these fields, the concept that time is not a simple, linear flow, but an emergent phenomenon arising from a sum over complex histories provides a guiding principle for deeper understanding. By embracing the path integral perspective, we are led to a vision of the universe as a dynamic, probabilistic ensemble of histories, with time as an emergent phenomenon rather than a fundamental backdrop. This view not only enriches our theoretical physics, but also invites profound philosophical reflection on the nature of existence, causality, and the flow of time. Ultimately, Feynman's path integral formulation reveals a cosmos where the familiar notion of time as a steady, unidirectional flow dissolves into a symphony of simultaneous possibilities, where every conceivable path contributes to the unfolding of reality. In this framework, the passage of time is not a fundamental truth, but a macroscopic illusion emerging from the quantum superposition of all possible histories. Next, we will delve into Tegmark's mathematical universe hypothesis, which proposes that reality itself is a mathematical structure and that time, like space, is embedded in this abstract mathematical entity. Max Tegmark's mathematical universe hypothesis presents one of the most radical and profound perspectives on the nature of reality and time. According to this hypothesis, the physical universe we inhabit is not just described by mathematics, but is mathematics at its core. Reality itself is a vast, timeless mathematical structure, and everything we experience, including time, is embedded within this abstract mathematical framework rather than existing independently or fundamentally. This concept challenges our everyday intuition by suggesting that what we call physical existence is a manifestation of pure mathematical relationships. In Tegmark's view, every mathematically consistent structure exists out there as a real entity. Our universe, with its familiar dimensions, laws of physics, and flow of time, is just one among potentially infinite such structures. From this standpoint, time is not a fundamental dimension that flows or progresses on its own. Instead, it is an emergent feature within the mathematical structure that gives rise to our perception of sequential events. Put simply, time arises from relationships and patterns within this eternal mathematical object, not the other way around. This perspective has its roots in the idea that mathematics is not merely a human invention or a descriptive tool, but an objective reality in its own right. Tegmark's hypothesis extends this idea by claiming that all possible mathematical structures exist equally and timelessly. Our universe's apparent dynamics, including the passage of time, are internal features of one specific mathematical structure that we happen to inhabit. Since mathematics itself exists outside of time, the flow we experience is a secondary, emergent phenomenon, much like a shadow cast by a three-dimensional object. One way to visualize this is to imagine a timeless four-dimensional block consisting of all events, past, present, and future, embedded in a mathematical entity. Just as a geometric shape exists timelessly in mathematics without changing, the universe's totality exists timelessly as a mathematical object. Our consciousness moves through this structure in a way that gives us the illusion of time flowing, but the structure itself remains static and unchanging. The mathematical universe hypothesis also provides an elegant explanation for why the laws of physics appear so precise and universal. If reality is a mathematical structure, then the laws governing it are simply the internal rules of that structure, not arbitrary conventions. This removes the mystery of why mathematics so effectively describes the physical world and why the constants of nature have the values they do. They are simply aspects of the underlying mathematical reality. Tegmark's view aligns with and extends earlier ideas from philosophers and physicists who have pondered the timeless nature of the universe. It shares similarities with the block universe theory, where time is a dimension and all moments exist simultaneously. However, Tegmark's idea is more foundational, positing that the universe is not just a four-dimensional space-time, but a more abstract mathematical entity from which space, time, and matter emerge. A crucial implication of this hypothesis is that our subjective experience of time's passage is a feature of consciousness within a mathematical structure rather than an external flow. Our brains, modeled as complex mathematical patterns within this structure, interpret and navigate the internal relationships that correspond to time. Thus, consciousness experiences time as a sequence of states within the structure, but this experience does not imply that time flows outside of that mathematical context. This hypothesis challenges the traditional ontological divide between the physical and the abstract. Instead of treating physical objects and time as fundamentally different from mathematical concepts, it collapses this distinction. Time, space, matter, and energy are all different aspects or facets of the same underlying mathematical reality. In addition, Tegmark's mathematical universe hypothesis touches on the question of the beginning of time. Since the mathematical structure is timeless and eternal, the question of a temporal beginning becomes moot. Our perception of a Big Bang or the universe's start is simply a feature embedded within the structure's internal relations, not a fundamental event outside it. Philosophically, this viewpoint leans toward a kind of Platonism, where abstract mathematical forms have a real and independent existence. It also aligns with ontological reductionism by reducing the complexity of the physical universe to mathematical relations and structures. The mathematical universe hypothesis inspires profound questions about the nature of free will, causality, and the meaning of existence. If all mathematical structures exist timelessly, then every possible universe with every possible history also exists, including versions of ourselves living different lives in alternate branches of this grand mathematical landscape. One challenge for this hypothesis is the apparent difficulty in explaining why we experience a well-defined flow of time, why causality appears directional, and why the universe has certain initial conditions. Tegmark and supporters suggest that these features emerge from the structure's internal consistency and the ways conscious observers experience it. But this remains a deeply open question. In terms of physics, Tegmark's hypothesis is extraordinarily difficult to test directly because it makes a metaphysical claim about the nature of reality beyond empirical measurement. However, it provides a framework that can unify many disparate theories and perspectives on time by framing them as different aspects or views of the underlying timeless mathematical structure. The hypothesis also resonates with other theories that propose time is emergent or illusory, like the emergent time hypothesis or the block universe, but goes further by asserting that the very foundation of all existence is mathematical and timeless. In summary, Tegmark's mathematical universe hypothesis paints a picture of a timeless reality where time does not flow, but is a static dimension within an eternal mathematical structure. Our experience of time's passage is an emergent phenomenon rooted in the internal relationships of this mathematical universe and in our conscious interpretation of these relationships. This viewpoint reshapes how we understand the nature of reality, bridging physics, philosophy, and mathematics into a singular vision of a universe where time, as we know it, is not fundamental but a feature of the timeless mathematical fabric from which everything arises. Next, we will explore Penrose's conformal cyclic cosmology, a theory proposing that the universe undergoes infinite cycles of birth, death, and rebirth, each cycle redefining time itself. Penrose's conformal cyclic cosmology, CCC, presents a captivating and deeply transformative view of a universe and the nature of time. According to this theory, proposed by the mathematical physicist Sir Roger Penrose, our universe is not a one-time occurrence with a definite beginning and an eventual end, but rather part of an infinite sequence of cosmic cycles. Each cycle beginning anew after the previous one has reached an ultimate state. In this model, the universe undergoes repeated eons, with each aeon representing a complete life cycle of the cosmos, from a Big Bang-like birth to a far future where expansion continues indefinitely. What makes this theory extraordinary is the idea that time itself resets or is redefined after every cycle, suggesting that time is neither linear nor permanent, but cyclical and emergent from deeper cosmic processes. Central to CCC is the notion that the universe's infinite expansion eventually leads to a state that is conformally invariant, meaning that the geometry of space-time at this far future can be rescaled so that it becomes indistinguishable from the universe's extremely dense and hot initial state. Effectively, the Big Bang of the next aeon. Conformal invariance is a powerful mathematical symmetry that preserves angles but not lengths, enabling the universe's infinitely expanded, cold, and sparse state to be mathematically transformed into the extremely hot and dense initial conditions of a new cycle. This transformation resets the clock of the cosmos, with time as we know it emerging anew in each cycle rather than persisting indefinitely. From the perspective of conformal geometry, the end of one universe and the beginning of another are connected seamlessly, but the usual notion of a linear timeline extending through these transitions does not hold. Instead, Time in CCC is cyclical, with each aeon having its own temporal flow that begins when the previous one ends. In other words, the arrow of time, which seems so fundamental to our everyday experience, is not a universal constant, but a property intrinsic to each individual aeon. When an aeon concludes, time is experienced within it effectively ends and then restarts in the new aeon. This challenges the traditional linear, unidirectional view of time rooted in classical physics and the everyday notion that the universe has a unique beginning and marches inexorably toward an end. Instead, CCC proposes a universe without a singular temporal origin or ultimate temporal destination. Time does not stretch infinitely in one direction, but renews itself cyclically. Each cycle encapsulates the entire cosmological history, making past and future cyclical in a grand cosmic sense. Penrose's CCC also offers a novel approach to some of the most puzzling questions in cosmology, such as the low entropy state of the early universe. The second law of thermodynamics, which states that entropy tends to increase, implies a time direction, the arrow of time. But why did the universe begin in such a low entropy state? CCC provides an answer by positing that the end of the previous aeon, after vast amounts of cosmic expansion and entropy increase, becomes the low entropy starting point of the next aeon due to the conformal rescaling process. This cyclical resetting of entropy is one of the theory's most significant claims, implying that what appears as a low entropy Big Bang is actually a transformed endpoint of an earlier universe. Moreover, the CCC model predicts observable signatures in the cosmic microwave background, CMB, the relic radiation from the early universe, such as concentric circles or specific patterns resulting from black hole collisions in the previous aeon. These predictions provide a potential empirical basis for validating or falsifying the theory, setting it apart from many other speculative cosmological ideas. In terms of the nature of time, CCC radically redefines temporal concepts. Since each aeon has its own intrinsic time parameter, and because the transition between eons is mediated by conformal geometry, time is neither absolute nor eternal. The flow of time exists only within individual cycles, and the cosmic timeline is composed of an infinite series of disconnected but conformally linked temporal domains. This cyclical model thereby undermines the traditional idea that time is a continuous, uniform dimension stretching from a singular beginning to an end. Philosophically, CCC resonates with ancient notions of cyclical time found in various cultures, but is grounded in rigorous modern physics and mathematics. It compels us to rethink the meaning of beginnings, endings, and the very fabric of reality itself, suggesting that existence is an eternal dance of cosmic cycles, each resetting the stage on which time unfolds. Importantly, the concept of resetting time in CCC aligns with the broader question of whether time is fundamental or emergent. CCC leans heavily toward time being emergent, arising from the changing conditions of the universe rather than existing as a fundamental backdrop. When one aeon ends and another begins, time, entropy, and the causal structure of the universe are all reshaped, reinforcing the idea that time is more a property of the universe's state than a permanent feature. This cyclic resetting also touches on the philosophical debate about permanence and change. If time renews with every cycle, then the permanence we attribute to time dissolves into a series of transient states, each temporary and dependent on the conditions of its aeon. The universe's history is not a single story unfolding linearly, but a series of overlapping narratives, each with its own temporal domain. Furthermore, CCC introduces intriguing implications for causality and the nature of cosmological events. If each aeon follows from the previous one, causal relationships extend beyond single cycles. But because time resets, the conventional notion of cause and effect across cycles becomes more subtle and complex. It raises the possibility that causality is confined to individual eons, with transitions mediated by deeper geometric principles rather than temporal continuity. CCC also dovetails with other modern theoretical frameworks that question the fundamental nature of time. For example, it complements ideas like the block universe, which sees all events as fixed in a four-dimensional spacetime, by proposing that the four-dimensional spacetime of each aeon is part of a larger, infinite series of conformally connected spacetimes. Similarly, CCC resonates with the notion that time may be an emergent property, as posited by the emergent time hypothesis, by emphasizing that time's arrow and flow are specific to each cosmic cycle. This theory further challenges the human perception of time as a linear progression. Our conscious experience, deeply rooted in a forward-moving timeline, corresponds only to the span of our current aeon. From the broader cosmic perspective, this linearity dissolves into an eternal loop of eons, where each moment is both a continuation and a new beginning. In addition, CCC has sparked ongoing debate and research within the physics community. While some find its mathematical elegance and explanatory power compelling, others point to the difficulty of confirming its predictions or reconciling it fully with quantum mechanics and other theories. Despite this, CCC remains a vibrant and influential theory pushing the boundaries of our understanding of time and the cosmos. In summary, Penrose's conformal cyclic cosmology offers a vision of the universe as an infinite sequence of cosmic cycles, each with its own intrinsic time, and where time resets after every cycle. This redefines time as neither linear nor permanent, but as an emergent, cyclical phenomenon intimately tied to the universe's geometry and entropy. The arrow of time exists within individual eons, but dissolves at their transitions, challenging fundamental assumptions about time's nature and suggesting a cosmos where beginnings and endings are continually reborn in an eternal, timeless dance. Next, we will explore time reversal symmetry, the idea that physical laws are symmetric in time, and what that means for the flow of time. Time reversal symmetry is a fundamental concept in physics that challenges our everyday understanding of time as an irreversible flow from past to future. It arises from the observation that many of the fundamental laws governing physical processes are symmetric with respect to time, meaning these laws work equally well if time were to run backward. In other words, the fundamental equations that describe how particles move, forces interact, and fields evolve do not inherently distinguish between the forward or backward direction of time. This symmetry suggests that at a fundamental level, the physical universe does not prefer a specific temporal direction, casting doubt on the notion that the flow of time we perceive is an objective feature of reality. To delve deeper, consider Newtonian mechanics and electromagnetism. Their governing equations are time reversal invariant. If you record a video of two billiard balls colliding and play it backward, the physics still makes sense. The interactions remain consistent with physical laws, and nothing about the reverse process violates those laws. Quantum mechanics also exhibits this symmetry in its fundamental equations, except for certain rare cases involving weak nuclear forces where a slight asymmetry has been observed. Still, the vast majority of interactions in nature obey time reversal symmetry, reinforcing the idea that the arrow of time is not encoded in the fundamental laws themselves. Yet, this symmetry stands in stark contrast to our experience of time as unidirectional. We witness eggs breaking but never spontaneously reforming, smoke dispersing rather than reassembling, and aging happening forward, not backward. This apparent contradiction is reconciled in part by the concept of entropy and the second law of thermodynamics, which introduces an arrow of time based on the increase of disorder. But the time reversal symmetry of fundamental laws remains a perplexing puzzle, suggesting that the macroscopic irreversibility we observe might emerge from underlying time-symmetric rules. The implications of time reversal symmetry are profound. If the laws of physics are indifferent to the direction of time, then the flow of time could be an emergent or even illusory phenomenon, arising from boundary conditions or statistical effects rather than fundamental physical principles. Time itself might be more akin to a parameter or coordinate that labels sequences of events rather than a physical entity flowing in one direction. This view aligns with certain interpretations of the block universe theory, where past, present, and future coexist in a four-dimensional space-time manifold, and time's flow is simply a feature of consciousness or perception, not of the universe itself. In such a framework, the universe is a static entity where all moments exist equally, and our sense of moving through time is an emergent phenomenon arising from our cognitive processes. Physicists have explored the ramifications of time reversal symmetry in many contexts, including particle physics and cosmology. For instance, violations of time reversal symmetry, T-violation, in weak interactions, discovered in experiments involving neutral kaons and B mesons, have sparked intense study because they might help explain the dominance of matter over antimatter in the universe. Yet these violations are subtle and localized, leaving the broader symmetry intact at most scales. At the quantum level, time reversal symmetry informs interpretations of the wave function and quantum processes. The possibility that quantum events are fundamentally reversible contradicts the classical idea of a temporal flow that irreversibly progresses. Quantum experiments, such as the delayed choice experiment and quantum erasers, reveal that measurements and observations can affect past states, further complicating the temporal picture and suggesting that time's arrow may be deeply intertwined with the act of observation and information. Moreover, the role of time reversal symmetry extends into thermodynamics and statistical mechanics. While microscopic physical laws are time-symmetric, macroscopic phenomena are not. The puzzle of how irreversible macroscopic behavior emerges from time-symmetric microscopic laws is a key question in understanding the nature of time. Various approaches, including the concept of coarse graining, where the detailed microstates are grouped into macrostates, help explain this emergence of directionality from underlying symmetry. Time reversal symmetry also influences cutting-edge theories in quantum gravity and cosmology. For example, certain approaches to unifying quantum mechanics and general relativity posit that time might not be a fundamental ingredient of the universe, but rather a secondary, emergent property that arises under specific conditions. In these contexts, time reversal symmetry plays a role in ensuring the consistency and reversibility of fundamental interactions. Philosophically, the idea that physical laws are time-symmetric challenges deeply held intuitions about causality and the temporal ordering of events. If the universe does not fundamentally distinguish past from future, then causality might be more about correlations and information flow rather than an intrinsic arrow of time. This challenges how we think about cause and effect, free will, and the structure of reality. Furthermore, time reversal symmetry raises questions about the nature of memory and experience. Since our memories and consciousness seem to operate in a time-directed way, recalling the past but not the future, this asymmetry might be a feature of the brain and its physical processes rather than an objective property of time itself. This aligns with ideas from neuroscientific studies showing that perception of time's flow could be a constructed experience, deeply tied to how our brains process sensory information. In the realm of cosmology, time reversal symmetry prompts questions about the initial conditions of the universe and the Big Bang. If physical laws are time-symmetric, then why does the universe appear to have a beginning with low entropy and a forward-moving arrow of time? The answer may lie in boundary conditions or deeper physical principles yet to be uncovered, which break the symmetry at large scales despite the underlying symmetrical laws. Experiments in quantum mechanics have also explored the consequences of time reversal symmetry. Quantum states and processes often exhibit reversibility in theory, yet the act of measurement introduces apparent irreversibility. This paradox, known as the measurement problem, hints at a fundamental interplay between time, observation, and information that remains unresolved. Some interpretations suggest that the universe's wave function evolves unitarily and symmetrically in time, but the collapse of the wave function during measurement introduces an effective arrow of time. This tension between symmetrical laws and asymmetrical phenomena continues to be an area of vibrant research. Time reversal symmetry also appears in advanced formulations of physics like the Wheeler-DeWitt equation and the Page-Wooters mechanism, where time is absent as a fundamental variable. These theories explore how temporal directionality can emerge from timeless quantum states, further underscoring that time's flow might not be a fundamental aspect of reality. In summary, time reversal symmetry reveals that the fundamental physical laws do not favor a direction of time, suggesting that the flow of time as we perceive it is not a basic feature of the universe, but a higher-level emergent phenomenon. This challenges the deeply ingrained intuition that time moves inexorably forward and compels us to rethink the relationship between time, causality, entropy, and consciousness. Whether time's arrow arises from boundary conditions, statistical effects, or cognitive processes, the symmetrical nature of physical laws points to a universe where time's flow might indeed be an illusion. Next, we will examine philosophical idealism, the view that reality is fundamentally mental and time may be a construct of consciousness. Philosophical idealism is a profound and ancient philosophical position that places consciousness or mind at the foundation of reality, suggesting that what we perceive as the external world, and crucially, time itself, is essentially a construct or feature of mental experience rather than an independent, objective entity. According to this view, time does not exist outside of perception. It arises only because conscious beings experience change and sequence events in their minds. Without a mind to observe and interpret, time would not have any meaning or existence. This idea runs counter to the common sense and scientific assumption that time is a physical dimension or universal flow independent of observers. Idealism's roots stretch back to philosophers like George Berkeley, who famously proposed that to be is to be perceived, meaning that existence depends on being experienced by a mind. When applied to the concept of time, this leads to the conclusion that time's passage, direction, and even its reality itself are tied fundamentally to the mental act of perceiving and remembering. Time, in this sense, is not a river flowing through the universe, but a mental framework that organizes sensory input and memories into an ordered sequence. The past, present, and future exist as mental constructs or narratives that consciousness generates to make sense of experience. One compelling aspect of philosophical idealism is how it explains the subjective nature of time. Human beings do not experience time uniformly. Moments can feel elongated or compressed depending on emotions, attention, or context. This subjectivity aligns well with the idea that time is not a fixed external property, but a flexible construct created by consciousness. For example, in moments of intense focus or danger, time may seem to slow down, while during boredom or routine, it appears to speed up. These experiences highlight the intimate link between time and the mind's interpretation of events. Idealism also provides a framework for understanding why time seems to have a direction from past to future, because the mind inherently organizes experiences in a causal narrative to make sense of reality. Memory plays a central role. We remember the past, but not the future, creating an arrow of time within the structure of consciousness. This arrow is less about physical processes and more about the mental ordering of events and the persistence of self through time. The implications of idealism extend into debates about free will, personal identity, and the nature of existence itself. If time exists only in the mind, then questions about determinism and causality become intertwined with the structure of conscious experience rather than objective external reality. The past, present, and future become mental constructs, potentially fluid and subject to reinterpretation, raising fascinating questions about whether the future is open or fixed. Philosophical idealism resonates with certain interpretations of quantum mechanics, where the role of the observer is central. Some interpretations suggest that physical reality is not fully determined until observed or measured, implying that consciousness plays a participatory role in shaping reality, including its temporal dimension. This echoes the idealist notion that time may arise from the mind's interaction with the physical world rather than existing as an independent parameter. In exploring this view, it's important to consider neuroscientific insights into how the brain constructs temporal experience. Our brains actively synthesize sensory information over short intervals to create a continuous sense of now and a coherent timeline. Studies show that this process involves complex mechanisms of memory, prediction, and attention, reinforcing that time, as we know, it is inseparable from cognitive function. From this perspective, time's flow is an emergent property of how our minds model and process experience, not a fundamental feature of the external world. Philosophical idealism also invites us to rethink the nature of reality itself. If everything we perceive, including space and time, depends on mind or consciousness, then the materialist view that the universe exists independently of observers is called into question. Reality becomes a mental construct or shared experience generated by consciousness. This radically shifts the ontological foundation from matter and energy to mind and perception. Historically, idealist thinkers such as Immanuel Kant proposed that time and space are forms of intuition, meaning they are ways our minds structure experience rather than features of things in themselves. Kant argued that time is a necessary condition for humans to organize sensory data, but it does not pertain to things as they exist independently of our perception. This philosophical groundwork supports the idea that time is not a fundamental part of external reality, but a mental framework. Despite its appeal, philosophical idealism faces challenges and criticisms, particularly from scientific realism, which holds that time is a physical dimension measurable and consistent across observers. Critics argue that idealism struggles to account for the objective regularities and predictable patterns of nature that do not depend on any particular observer's mind. Additionally, scientific findings like time dilation and relativity demonstrate that time behaves in precise, measurable ways independent of human perception. However, proponents of idealism respond by emphasizing that even scientific measurements are ultimately interpreted through conscious experience, suggesting that science itself presupposes a mental framework. They argue that idealism does not deny the consistency of physical laws, but reframes them as descriptions of phenomena within conscious experience, not of an independent, mindless universe. Philosophical idealism's approach to time dovetails with ongoing debates in the philosophy of mind, especially regarding the nature of consciousness and its relationship to physical reality. If consciousness is fundamental and time arises from it, then understanding time fully requires grappling with the mysteries of subjective experience, a challenge that remains at the frontier of philosophy and cognitive science. Moreover, idealism invites a reconsideration of the nature of causality. If time is a mental ordering, then causal relationships may not be absolute features of the universe, but rather ways the mind connects events to make sense of the world. This challenges the standard temporal cause-effect paradigm, potentially allowing for alternative conceptions of causation that are less bound by linear time. In summary, philosophical idealism proposes that time is not an external, objective dimension, but a feature of mind or consciousness, constructed to organize sensory experience and memory. This view explains the subjective nature of time, the directionality of temporal experience, and a central role of observation and cognition in shaping reality. While it confronts challenges from scientific realism, it remains a compelling perspective that pushes us to reconsider the fundamental nature of time and reality. Next, we will explore the holographic principle, a theory proposing that the universe's information, including time, is encoded on a lower dimensional boundary, challenging the fundamental nature of space-time. The holographic principle is a revolutionary concept in theoretical physics that challenges our traditional understanding of space and time, suggesting that these dimensions might not be fundamental realities, but rather emergent phenomena, projections from a deeper, lower-dimensional reality. Originating from studies of black hole thermodynamics and quantum gravity, The principle posits that all the information contained within a volume of space can be described entirely by information encoded on the boundary of that region, which is one-dimensionless. In simpler terms, our three-dimensional universe, including space and time, could be akin to a hologram projected from a two-dimensional surface. This idea first gained prominence through the work of physicists Gerard T. Hooft and Leonard Susskind, who investigated the paradoxes surrounding black holes. When matter falls into a black hole, the information about that matter seems to vanish, violating quantum theory's fundamental tenet that information must be conserved. The holographic principle resolves this by proposing that the information is not lost, but encoded on the black hole's event horizon, a two-dimensional surface enveloping the black hole, implying that the bulk volume of space inside the black hole can be fully described by data on this boundary. Extending this to the entire universe leads to the mind-bending suggestion that everything we experience, our three-dimensional spatial reality and the progression of time, could be the emergent shadow of processes occurring on a distant two-dimensional boundary. This radically reframes time's nature, suggesting it may not exist as a fundamental dimension flowing inexorably forward, but as an emergent property arising from the way information is arranged on this holographic surface. One of the most fascinating aspects of the holographic principle is how it bridges gravity and quantum mechanics, two pillars of physics that traditionally have been difficult to reconcile. Gravity, which governs large-scale structures and shapes space-time, appears classical and continuous, whereas quantum mechanics governs the probabilistic and discrete behavior of particles on the smallest scales. The holographic approach offers a framework where quantum information encoded on a lower dimensional boundary manifests as gravitational dynamics in the higher dimensional bulk, including the emergence of time as part of that geometric structure. The principle also connects closely with the ADS/CFT correspondence, a specific realization proposed by Juan Meldacena in the late 1990s. In this framework, a gravitational theory defined within a volume of anti de Sitter, ADS, space corresponds exactly to a conformal field theory, CFT, without gravity on the boundary of that space. Here, time and space within the ADS bulk emerge from a timeless quantum field theory on the boundary. This is a concrete example of how time might not be fundamental, but instead a derived, emergent aspect of a deeper, more abstract reality. This holographic viewpoint shakes the foundations of how we conceive reality. It suggests that what we perceive as a flowing time and tangible spatial dimensions are not fundamental entities, but informational constructs. If the universe is fundamentally two-dimensional and timeless, then our experience of moving through time could be a cognitive artifact of interpreting this holographic projection. In practical terms, the holographic principle may imply limits on the nature of physical information and the smallest scales of space and time, hinting that space-time itself has a discrete, pixelated nature akin to a digital image projected from surface. This resonates with other theories proposing quantization of space-time and supports the idea that space and time lose their usual meaning at the Planck scale, where quantum gravity effects dominate. Moreover, the holographic principle challenges the conventional view of locality, the idea that objects are only directly influenced by their immediate surroundings. If all information is encoded on a distant boundary, then what happens here might be fundamentally linked to what happens there on the boundary surface, potentially accounting for the non-local phenomena observed in quantum entanglement. The implications for time are particularly profound. Since time appears as part of the emergent geometry in the bulk space, it may not have a standalone existence independent of this holographic information encoding. Time's arrow, flow, and even its dimension might be a byproduct of the underlying information processing on the two-dimensional boundary, raising the possibility that the universal experience of temporal passage is an emergent illusion, much like a three-dimensional hologram emerging from a flat surface. This principle also dovetails with certain philosophical perspectives that see reality as fundamentally informational or computational. If the universe is a holographic projection of information encoded at a deeper level, Then information, the patterns and relationships that define states of existence, becomes the core substance of reality. Time, then, is simply one way these informational patterns manifest to conscious observers embedded in the holographic projection. In addition, the holographic principle has inspired new directions in understanding the nature of black holes and the universe's ultimate fate. Since time is tied to space-time geometry, changes in the holographic boundaries information content could drive cosmic evolution, including phenomena such as cosmic expansion and possibly the Big Bang itself as a boundary condition in this informational framework. From a scientific standpoint, while the holographic principle remains a theoretical and mathematical framework, it has gained substantial traction due to its ability to unify disparate areas of physics and resolve long-standing paradoxes. Its predictions and models are being actively explored in cutting-edge research, although direct experimental verification remains a challenge due to the extreme scales involved. In philosophical terms, the holographic principle challenges us to rethink what it means to exist in time and space. If these dimensions are emergent rather than fundamental, then reality, as we know, is deeply intertwined with the structure and processing of information on a surface beyond our direct experience. This challenges the notion of an objective, absolute time and opens the door to novel conceptions where the flow of time is a secondary effect of deeper, timeless laws encoded holographically. The principle also intersects with human perception and consciousness. Our brains interpret sensory data that presumably come from this holographic projection, organizing experiences into a continuous narrative of time and space. If the underlying reality is a timeless information pattern, then the subjective experience of time's flow is a construction by consciousness to navigate this encoded universe effectively. Furthermore, the holographic principle is part of a broader movement in theoretical physics that views reality through the lens of information theory. Concepts like entropy, quantum entanglement, and computational complexity become fundamental in describing the universe, suggesting that understanding time requires grappling with these informational processes rather than relying solely on classical notions of clocks and events. In summary, the holographic principle offers a radical and elegant perspective on the nature of time, proposing that time and space are not intrinsic aspects of reality, but emerge from information encoded on a two-dimensional boundary. This profound idea challenges conventional wisdom, suggesting that our everyday experience of time is a projection from a deeper, timeless informational substrate. It links the macroscopic geometry of space-time with a microscopic quantum world, offering a potential path toward unifying physics and deepening our understanding of time as a complex, emergent phenomenon. Next, we will delve into information-theoretic time, a theory that explores how time may be rooted in the processing and flow of information itself. Information-theoretic time offers a captivating framework that reinterprets time not as an inherent dimension of the universe, but as an emergent property arising from the flow and processing of information. This perspective aligns with the growing realization in physics and philosophy that information, the abstract content, patterns, and relationships encoded in physical systems, may be more fundamental than space or time themselves. The key idea here is that what we perceive as time could be a reflection of how information is communicated, transformed, and updated throughout the universe, rather than a backdrop or container in which events unfold. At its core, information-theoretic time suggests that temporal order and the sensation of time's flow emerge from the causal structure of information exchange. Systems that process and transmit information impose a directionality, what physicists often refer to as causality, that naturally gives rise to the distinction between past, present, and future. Unlike traditional models of time that treat it as a smooth continuum or a geometric dimension, this approach views time as the consequence of changes in informational states, akin to the ticking of an abstract clock built from bits of data changing and evolving. This concept resonates strongly with the thermodynamic arrow of time, where the direction of increasing entropy corresponds to a growing amount of disorder or information uncertainty in the system. However, information-theoretic time extends beyond thermodynamics, proposing that the very structure of causality and temporal sequencing in the universe might be encoded in information networks themselves. The way bits of information influence one another, the ordering of computational events, and the propagation of signals collectively give rise to the experience of time. One of the most compelling motivations behind this theory comes from quantum mechanics and the quest for quantum gravity, where conventional notions of space-time break down at the Planck scale. In such regimes, space-time geometry may not be well defined, but information flow, encoded in quantum states, entanglement patterns, and interactions, remains meaningful. Consequently, physicists exploring quantum gravity and related fields consider information as the primary substrate from which space-time and time emerge as macroscopic, approximate phenomena. The theory also suggests that different observers, depending on their informational access and the causal structure they inhabit, may experience time differently. This aligns with relativistic principles where observers moving relative to each other or in different gravitational fields experience different rates of time passage. Yet, information-theoretic time frames these differences in terms of variations in information flow and causal connectivity rather than invoking time as a fundamental backdrop. From a computational perspective, one can envision the universe as a vast information processing system or quantum computer, where physical processes correspond to computations, and time is the sequence of computational steps. This analogy illuminates how time might be emergent. Just as the running of a computer program depends on sequential operations on data, the flow of time corresponds to the ordering of informational updates in the cosmos. Further, this approach to time ties into ideas from digital physics and algorithmic information theory, which propose that physical reality is underpinned by discrete informational units, bits or qubits, processed according to fundamental computational rules. In this context, time does not exist as a continuous dimension, but as discrete updates in the informational state of the universe. Much like frames in a digital video, give the illusion of smooth motion. Moreover, information-theoretic time intersects intriguingly with theories of consciousness and perception. Human awareness, memory formation, and the brain's integration of sensory inputs rely fundamentally on processing and ordering information. Our subjective experience of time, including the sense of continuity and causality, may reflect the brain's interpretation of underlying informational flows, reinforcing the idea that time is a cognitive construct rooted in information dynamics. One challenge in formalizing information-theoretic time lies in rigorously defining the mechanisms by which information flow generates a universal temporal order. Unlike the relatively straightforward geometric definition of time and relativity, this theory requires a deep understanding of causal networks, quantum correlations, and information entropy. Researchers employ tools from quantum information theory, network theory, and statistical mechanics to model how complex informational structures give rise to time's emergent properties. Importantly, this view provides a natural explanation for the arrow of time without needing to invoke special initial conditions or external parameters. The asymmetry in information flow, causal influences moving from past states to future states, naturally produces the irreversibility observed in macroscopic processes, aligning with the irreversible increase in entropy in thermodynamics and the unidirectional formation of memories in biological systems. Additionally, information-theoretic time reframes paradoxes that arise in conventional time theories. For example, the problem of time in quantum gravity, where traditional time disappears from fundamental equations, is resolved by recognizing that time is not a fundamental parameter, but an emergent phenomenon linked to how information is extracted and organized in different contexts. This theory also hints at profound implications for the nature of causality. If time emerges from information flow, then cause and effect are deeply entwined with how informational states propagate. Quantum entanglement, non-local correlations, and phenomena like retrocausality can be reinterpreted as manifestations of complex informational patterns that do not necessarily adhere to classical, linear temporal order. Moreover, information-theoretic time dovetails with the holographic principle and the concept that the universe's fundamental description might be informational rather than geometric. In this light, space-time and time emerge from a more abstract informational code, much like the holographic encoding on a boundary surface that projects our perceived universe. The theory also invites reconsideration of cosmological questions such as the Big Bang and the ultimate fate of the universe. If time emerges from information flow, then the origin of time corresponds to a fundamental shift in informational structure, possibly linked to the initial conditions of the universe or a phase transition in the cosmic informational network. On the practical front, efforts to unify quantum mechanics and gravity increasingly explore informational foundations, suggesting that understanding the flow of information at the Planck scale could unlock a consistent theory of quantum gravity. Experiments in quantum information processing, quantum computing, and high-energy physics continue to probe these ideas, aiming to uncover signatures of emergent time or informational causality. From a philosophical standpoint, information-theoretic time resonates with process philosophy, which emphasizes becoming and change as fundamental, viewing reality as a dynamic flow of events rather than static entities. It also aligns with certain interpretations of quantum mechanics, like relational quantum mechanics, where the properties of systems, including time, depend on the relationships and information shared among observers. In sum, information-theoretic time radically reimagines time as a derivative concept emerging from the fundamental processes of information flow and causality. It challenges the traditional view of time as a backdrop against which events occur, instead proposing that the very structure and experience of time arise from the intricate dynamics of information in the universe. This perspective not only aligns with cutting-edge developments in physics, but also provides a rich conceptual framework bridging physics, computation, and philosophy. Next, we will explore digital physics, which builds upon the idea of the universe as fundamentally informational but emphasizes discrete, computational underpinnings of time and reality. Digital physics proposes a radical rethinking of the very fabric of reality, suggesting that the universe operates fundamentally like a vast computational system. In this view, the laws of physics are akin to computer code, and the evolution of the universe is a process of information being processed step by step. Time, then, is not an independent, continuous dimension as traditionally conceived, but rather a discrete sequence of computational operations, akin to the ticks of a cosmic clock embedded in the processing of information. This theory draws from advances in both theoretical physics and computer science. It argues that space, time, matter, and energy emerge from the processing of bits, or, more accurately in quantum contexts, qubits. The universe, on the smallest scales, behaves like a quantum computer with its state updated in discrete intervals. Time's apparent flow corresponds to the sequence of these updates, meaning that the passage of time is fundamentally tied to the progression of computational steps. Thus, rather than time being a fundamental dimension through which events unfold, it is the byproduct of a deeper, more abstract computation running beneath physical reality. One compelling motivation for digital physics comes from the inability of continuous models to reconcile quantum mechanics and gravity. At the Planck scale, where quantum effects dominate, space and time seem to lose their smoothness, suggesting a granular, discrete structure. This discreteness aligns naturally with a computational model, where each update represents a new frame in the cosmic algorithm. Digital physics thus provides a promising framework to unify physics by casting it as information processing at a fundamental level. The notion that time emerges as a step in this cosmic computation also sheds light on the puzzling features of quantum mechanics, such as superposition and entanglement. In a digital universe, these phenomena may be understood as the state of a quantum register in the computational process. The seemingly continuous flow of time experienced by conscious beings emerges from the discrete updates of the underlying quantum computation. Furthermore, this viewpoint challenges the classical idea of continuity in time and space. Instead of viewing reality as a smooth continuum, digital physics describes it as a network of discrete, digital events, much like the pixels on a screen or the frames of a digital video. Our perception of smooth time flow arises from the incredibly rapid and fine-grained processing of these fundamental steps, creating an illusion of continuity. An important implication of digital physics concerns determinism and randomness. If the universe is a computation, its rules are specified by an underlying program. However, this does not necessarily mean the universe is fully deterministic. Quantum computation and randomness may be integrated into the cosmic algorithm, with probabilistic processes encoded within the computation itself. This introduces an intriguing balance between deterministic rule-following and inherent randomness, shaping the unfolding of time as perceived. Digital physics also provides a fresh lens to view well-known paradoxes and phenomena involving time. For instance, time dilation effects observed in relativity can be interpreted as variations in the processing rate of the universal computation. Just as a computer might slow down when handling more complex data or under heavier computational loads, physical processes in strong gravitational fields or at high velocities experience a slower tick rate in their local informational updates. Moreover, the theory aligns with ideas from cellular automata and lattice models proposed in physics, where space and time evolve according to discrete rules on a grid or network. These models simulate how complex structures and behaviors can emerge from simple, local computational rules iterated over discrete time steps, mirroring the digital physics concept at a fundamental level. The digital universe hypothesis also prompts us to rethink the nature of causality and the arrow of time. Since time corresponds to steps in a computation, causality is built into the program's logic. Each step depends on the prior state, ensuring a consistent order of cause and effect. This inherent causal structure naturally produces the temporal ordering we observe, reinforcing the flow of time without requiring it as a fundamental backdrop. At the cosmological scale, digital physics offers fascinating possibilities. The Big Bang might be seen as the initial input or boot up of the cosmic computation, from which all subsequent updates, the passage of time, and evolution of the universe flow naturally. Similarly, the end state of the universe could correspond to the halting or transformation of this computation, with time ceasing to exist beyond that point. Another profound consequence concerns consciousness and perception. If the universe operates as a quantum computer, human cognition and awareness might also be forms of information processing occurring within this grand computation. Our experience of time, the subjective now, the flow of moments, could be interpreted as the brain's synchronization with the underlying computational rhythm of the universe. This perspective also intersects intriguingly with the simulation hypothesis, which proposes that our reality might be a simulation run by an advanced intelligence. Digital physics offers a scientifically grounded framework to conceptualize such a simulation, describing how time and reality could arise from computational processes governed by an underlying program. Whether or not we live in a simulation, the idea that reality itself is computational underscores the profound link between information, computation, and time. Digital physics also fosters novel approaches to tackling some of physics' deepest problems. By modeling space-time as a computational network, researchers explore how quantum gravity might emerge from discrete, algorithmic structures. Techniques from quantum information theory and computational complexity increasingly inform these efforts, helping physicists uncover the informational architecture underlying space-time and time. Critics of digital physics raise questions about the testability of the theory and its metaphysical implications. If the universe is a computation, what is the hardware running it? Is the computational substrate itself physical, or is it a purely abstract entity? These questions challenge the boundaries between physics, philosophy, and metaphysics, inviting deep reflection on the nature of reality itself. Despite these challenges, digital physics remains a vibrant and growing area of inquiry. It synthesizes insights from physics, computer science, and philosophy, offering a unified language to describe the emergence of time and space from information processing. It underscores that what we perceive as the passage of time may be nothing more than the ticking of a cosmic computational clock, an emergent property of an underlying quantum algorithm. In summary, digital physics redefines time as a sequence of discrete computational steps that underpin the evolving state of the universe. This conception aligns naturally with modern physics efforts to reconcile quantum mechanics and gravity, and it provides a compelling framework to understand the origin, nature, and experience of time. The flow of time, rather than being a fundamental backdrop, is instead a dynamic product of a universe's ongoing computation, an idea that profoundly challenges and enriches our understanding of reality. Next, we will examine spontaneous collapse theories, which propose mechanisms for the transition from quantum timelessness to the classical experience of time. Spontaneous collapse theories represent a fascinating attempt to address one of the most perplexing puzzles in modern physics: how the definite, classical world we experience emerges from the underlying quantum realm, which is inherently probabilistic and seemingly timeless. At the heart of these theories lies the idea that the wave function, a mathematical description of a quantum system's multiple possible states, doesn't just evolve smoothly and deterministically as prescribed by the Schrödinger equation, but rather undergoes sudden, spontaneous collapses. These collapses reduce the myriad of quantum possibilities into a single definite outcome, and it is in this process that the illusion of time's flow might emerge. According to standard quantum mechanics, systems exist in a superposition of all possible states until an observation or measurement collapses this superposition into one reality. However, this traditional viewpoint raises the infamous measurement problem. What exactly causes or triggers this collapse, and why does it happen at a particular moment? Spontaneous collapse theories propose that this collapse isn't dependent on an external observer or measurement, but occurs randomly and intrinsically over time, governed by precise probabilistic rules. This intrinsic randomness introduces a temporal aspect, a progression from possibilities to actualities, effectively weaving time into the quantum fabric. One prominent example of such a theory is the Gerardo-Mini-Weber (GRW) model, which posits that the wave function of particles occasionally undergoes spontaneous localization events at random intervals. These localization events suppress the quantum superposition from macroscopic objects, thereby producing the classical definiteness we observe. In this framework, time isn't just a static backdrop. The unfolding of collapse events imbues the universe with a sense of becoming, a temporal evolution from quantum potentialities to concrete realities. Spontaneous collapse theories thus provide a mechanism for reconciling quantum timelessness, where all quantum states coexist in a timeless superposition, with our lived experience of a flowing time marked by distinct events. By transforming indeterminate quantum states into definite classical states in a time-dependent manner, these collapses generate an emergent arrow of time, giving the sensation of temporal progression. The before and after distinction becomes meaningful only as collapse events successively reduce possibilities to realities. This view aligns intriguingly with thermodynamic time, as the gradual collapse of quantum states tends to increase entropy, reinforcing the unidirectional arrow of time. The process of collapse itself can be interpreted as a transition from lower to higher entropy configurations, a physical manifestation of the passage from quantum ambiguity to classical certainty. It suggests that time's arrow may be deeply connected to the physical processes underlying quantum state reduction. From a philosophical standpoint, spontaneous collapse theories challenge traditional notions of determinism and objectivity. If collapses occur spontaneously and randomly, the evolution of a universe contains fundamental unpredictability. Time, therefore, isn't a smooth, deterministic flow, but a sequence punctuated by indeterminate events where possibilities become realities. This inherent randomness is essential in generating the temporal structure of experience. Moreover, the timing and frequency of these collapse events are not arbitrary, but linked to the scale and complexity of the systems involved. While microscopic particles may exist in superpositions for long periods, macroscopic systems rapidly collapse into definite states, ensuring the stability of the classical world we inhabit. This scale-dependent behavior explains why time appears continuous and well-defined at human scales despite the underlying quantum indeterminacy. Spontaneous collapse theories also intersect with consciousness and the measurement problem in intriguing ways. Some interpretations suggest that the process of collapse might be related to or even dependent on conscious observation, though spontaneous collapse models aim to avoid this by making collapse objective and observer-independent. Nevertheless, the connection between collapse and the perception of time remains an active area of debate and research. Experimental efforts to test spontaneous collapse models are underway, focusing on detecting deviations from standard quantum predictions. These experiments often involve ultra-sensitive measurements of superpositions in large molecules or tiny mechanical oscillators. Confirming spontaneous collapse would revolutionize our understanding of time, quantum mechanics, and the emergence of classical reality. Another implication of these theories concerns the nature of causality and temporal order. Since collapses occur in a time-dependent sequence, they provide a natural direction to cause and effect, embedding an intrinsic temporal asymmetry into the quantum world. This contrasts sharply with the time-symmetric laws of physics at fundamental levels and suggests that time's arrow arises from the physical mechanisms of collapse rather than from abstract symmetries. Furthermore, the process of collapse aligns well with the notion that time may be fundamentally discrete. Each collapse event marks a distinct update in the universe's quantum state, akin to frames in a movie reel. The flow of time emerges as a succession of such discrete events rather than a continuous stream, offering a bridge between quantum discontinuities and classical continuity. Spontaneous collapse theories also relate to other interpretations of quantum mechanics, such as the many-world interpretation, which denies collapse altogether by positing branching parallel universes. In contrast, collapse theories insist that the quantum wave function's reduction is real and unique, giving a single, consistent history of events with a well-defined temporal order. These theories impact how we consider the concept of past, present, and future. The past consists of outcomes already realized through collapse. The present is the moment at which the next collapse occurs, creating a new reality. And the future remains a realm of possibilities not yet collapsed. In this sense, time's passage is the continual actualization of potential quantum states. The emergence of classical spacetime itself may be linked to these collapse processes. Some physicists speculate that the geometry of spacetime and the flow of time arise from the fundamental act of wave function collapse, suggesting that spacetime is not a pre-existing stage but a dynamic outcome of quantum events. Additionally, these ideas intersect with the study of decoherence, where interactions with the environment effectively collapse quantum states by entangling them with surroundings. While decoherence explains the loss of quantum coherence, spontaneous collapse introduces an objective, physical collapse mechanism independent of environment, reinforcing the arrow of time. Philosophically, spontaneous collapse lends support to a dynamic view of reality where the future is open and becomes fixed only as collapses occur. This contrasts with static block universe models that see past, present, and future as equally real and fixed. Collapse theories thereby restore a form of temporal becoming and novelty to the unfolding universe. In terms of cosmology, spontaneous collapse may explain the emergence of classical spacetime from a quantum gravitational regime. As the early universe cooled and expanded, collapse events could have solidified the classical geometry and temporal order we observe today. Overall, spontaneous collapse theories offer a compelling explanation for why we experience a flowing time despite the timeless nature of fundamental quantum laws. By introducing objective, random collapses of the quantum state, these theories provide a physical foundation for the emergence of time's arrow and the classical world, revealing time itself as an emergent phenomenon born from the quantum substratum of reality. Next, we will explore Parmenides' timeless reality, an ancient philosophical viewpoint positing that time and change are illusions and that reality is fundamentally unchanging and eternal. Parmenides, a pre-Socratic philosopher from ancient Greece, presents one of the earliest and most profound conceptions of timeless reality, which has echoed through philosophy and even modern physics. His radical assertion is that change, motion, and temporal passage are illusory, and that the true nature of reality is a singular, eternal, unchanging whole. According to Parmenides, the world as it appears to us, dynamic, evolving, transient, is a deceptive facade, masking a deeper truth. Being simply is, and it always is. There is no coming into being or passing away, no before or after. Everything that exists is a unified, timeless existence. This concept of timelessness fundamentally challenges everyday experience, where change seems undeniable. However, Parmenides argues that if something truly changes, it must either come from nothing or turn into nothing, which he finds logically impossible. To exist at one moment and not at another violates the principle of non-contradiction. Therefore, change cannot be real in any fundamental sense. Instead, the appearance of change is a trick of perception, a consequence of our limited viewpoint embedded in time. True reality transcends time and remains a constant, immutable being. Parmenides' timeless reality has profound philosophical implications. It suggests that time itself is not a fundamental feature of the universe, but a derivative illusion arising from human consciousness or sensory experience. Time, with its flow and succession, is like a shadow cast on the wall of a deeper, changeless reality. This view aligns with many mystical and metaphysical traditions that emphasize eternal oneness over fragmented temporality. This timeless ontology challenges scientific approaches that rely on change and temporal evolution to describe natural phenomena. Yet, interestingly, modern theoretical physics often grapples with similar notions. In quantum gravity and cosmology, some models imply a timeless fundamental structure underlying the dynamism we observe. The idea that space-time and change emerge from a more basic, timeless entity resonates with Parmenides' vision. Parmenides' philosophy also introduces the idea that reality is holistic and indivisible. Change implies division, fragmentation, and multiplicity. If reality is truly eternal and unchanging, it must be a seamless unity. This idea anticipates modern holistic approaches in physics, such as entanglement and non-locality, which reveal interconnectedness beyond apparent separations. His argument against the reality of void or nothingness complements this worldview. For Parmenides, nothingness cannot exist because it is literally nothing. Since change would require something to come from or go into nothingness, change is logically incoherent. This stance forces reconsideration of how concepts like creation, destruction, and transformation are framed within the bounds of logic and ontology. Parmenides' timeless reality raises questions about the nature of perception and cognition. If time and change are illusions, how do conscious beings experience them so vividly? This invites exploration into the neurological and psychological processes that construct the flow of time from static inputs. Our minds might be wired to parse existence into discrete moments, creating a narrative of past, present, and future where none fundamentally exist. The philosophy of Parmenides also influences metaphysical debates on identity and persistence. If nothing truly changes, then the identity of objects and beings remains fixed eternally. This contrasts with common sense views that define identity through change and continuity. Parmenides invites a reconsideration of what it means for something to be beyond temporal markers. Moreover, his timeless reality problematizes causality. Cause and effect inherently depend on temporal order, one event preceding another. If time is illusory, causality too becomes suspect. This parallels challenges in physics, where quantum entanglement and non-locality seem to violate classical causal structures. Parmenides' insights prefigure such puzzles about the fundamental structure of reality. His ideas have inspired numerous philosophical and scientific explorations into the nature of time. From eternalism in modern metaphysics, where past, present, and future are equally real, to contemporary theories of block universes, echoes of Parmenides' unchanging whole are evident. These frameworks view time not as a flowing river, but as a landscape, a block where all events coexist timelessly. While Parmenides' timeless reality might seem counterintuitive or even nihilistic, it invites deep reflection on the assumptions underlying our experience of time. By questioning the reality of change and time itself, he opens pathways to new understandings of existence, consciousness, and the cosmos. In modern physics, attempts to reconcile quantum mechanics and general relativity often reveal hints that space-time may emerge from a deeper timeless substrate, echoing Parmenides' eternal is. This raises the possibility that the laws of physics we observe govern patterns within this timeless whole, rather than a universe that fundamentally evolves. The paradox of how to reconcile the undeniable experience of temporal flow with an underlying timeless reality remains one of the greatest challenges in philosophy and science. Parmenides' timeless reality offers a radical, foundational perspective that continues to provoke and inspire thinkers. Parmenides forces us to reconsider whether time is a fundamental constituent of a universe or merely a feature of human consciousness and perception. If his view holds, then the universe is true, nature is a changeless, eternal reality, of which our experience of passing time is only a surface phenomenon. This conception shifts the focus from temporal dynamics to a more static, holistic vision of being. It challenges the scientific worldview to account for the illusion of time's passage without assuming its fundamentality. In conclusion, Parmenides' timeless reality remains a powerful and provocative lens through which to view the enigma of time. His assertion that change and time are illusory invites a profound re-examination of the nature of existence itself. The timeless whole he describes is a foundational concept that continues to echo across philosophy, physics, and metaphysics, reminding us that beneath the flow of time, there may lie an unchanging, eternal reality that transcends all temporal illusions. Next, we will move into ontological reductionism, a theory that attempts to explain time by reducing it to more fundamental elements of reality. Ontological reductionism is a philosophical approach that seeks to understand complex phenomena by reducing them to their most basic, fundamental components. When applied to the concept of time, this theory proposes that what we experience and interpret as time is not a fundamental feature of reality itself, but rather an emergent property arising from more basic, non-temporal phenomena. According to ontological reductionism, time can be broken down and explained in terms of simpler, timeless elements, such as spatial configurations, causal relations, or informational structures. This perspective challenges the intuitive notion that time flows independently as a backdrop against which events unfold. Instead, it suggests that time is derivative, constructed from underlying features that themselves do not depend on the passage or existence of time. For example, temporal ordering might be reducible to a sequence of cause and effect relationships, or to patterns in the changing configurations of the universe's fundamental building blocks. In this view, time as a separate entity disappears, replaced by a network of static, atemporal facts. One of the key motivations behind ontological reductionism is the desire for a unified, simpler understanding of reality. Complex concepts, especially those as elusive and puzzling as time, can often obscure the true nature of the universe. By reducing time to non-temporal elements, scientists and philosophers hope to strip away these layers of complexity and reveal a more fundamental structure beneath. This approach aligns with the broader scientific goal of reducing diverse phenomena to a set of basic principles or laws. In the context of physics, ontological reductionism often intersects with attempts to develop a theory of quantum gravity. Since classical notions of time break down under extreme conditions like black holes or the Planck scale, researchers seek more foundational explanations. Some models propose that space-time itself is not fundamental, but emerges from underlying discrete or non-temporal entities. These entities might be quantum states, spin networks, or causal sets, structures that do not inherently possess time, but whose interactions give rise to temporal phenomena as emergent features. From a philosophical standpoint, ontological reductionism also prompts a re-evaluation of how humans perceive and understand time. Our mental constructs of past, present, and future might correspond to certain arrangements or informational states rather than to a flowing, objective temporal dimension. This implies that our experience of time is contingent upon the brain's processing of non-temporal information, further supporting the idea that time does not exist independently out there in the universe. Critics of ontological reductionism argue that reducing time to non-temporal phenomena risks oversimplification. Time, they contend, has unique qualities, such as its apparent directionality, its role in causation, and its intimate connection with consciousness, that might not be fully explained by reduction to simpler elements. These critics suggest that time may be irreducible, a fundamental aspect of reality that requires its own explanatory framework rather than being dismissed as an emergent illusion. Nevertheless, the ontological reductionist view has gained traction due to its promise of resolving paradoxes related to time. For instance, if time is not fundamental, problems such as the nature of the beginning of the universe or the reconciliation of quantum mechanics with general relativity may be better addressed. By shifting the focus to timeless entities and relationships, researchers may unlock new insights into the fabric of reality. One interesting implication of ontological reductionism is its impact on the concept of temporal flow. If time is not fundamental, the sense that moments flow from past to future is likely a psychological or emergent phenomenon, not an objective feature of the universe. This challenges deeply ingrained intuitions about time, demanding a radical rethinking of how events and changes are experienced and described. Furthermore, ontological reductionism often intersects with the philosophy of mind and cognitive science. Understanding how the brain constructs the experience of time from atemporal inputs or processes is an ongoing scientific endeavor. This approach supports the idea that temporal perception is a product of complex cognitive functions, built upon simpler informational and physical substrates that themselves lack inherent temporality. In addition, ontological reductionism opens avenues for exploring how other seemingly fundamental features, such as causality, space, and even consciousness, might be interrelated and reducible. If time can be explained through reduction, it raises the question of whether reality is ultimately a tapestry woven from timeless building blocks, where what we perceive as dynamic processes emerge from static configurations. This theory also resonates with certain interpretations of quantum mechanics, especially those emphasizing the role of information and correlations rather than temporal evolution. For example, quantum entanglement can connect particles instantaneously across distances, seemingly independent of time's flow. Such phenomena suggest that the foundational level of reality might operate outside of time, consistent with an ontological reductionist view. From a metaphysical perspective, ontological reductionism may be seen as an extension of classical reductionist philosophy, which has historically sought to explain complex natural phenomena through their constituent parts. It challenges the notion of time as a primitive concept, instead proposing it as a derived, secondary aspect of the universe's deeper structure. Importantly, This approach requires a redefinition of what we mean by existence and change. Without time as a fundamental axis, existence becomes a matter of configurations and relationships, not events occurring in temporal sequence. Change becomes a description of differences between states rather than a process unfolding through time. This conceptual shift can be difficult to grasp, but is crucial for fully embracing ontological reductionism. Moreover, ontological reductionism has implications for the philosophy of science. If time is emergent and reducible, scientific theories must adapt to describe not only phenomena within time, but also the underlying timeless reality from which time arises. This demands new mathematical frameworks and conceptual tools that transcend classical temporal descriptions. In sum, ontological reductionism offers a compelling lens through which to examine the nature of time. By proposing that time can be reduced to more fundamental, non-temporal phenomena, it challenges conventional views and opens up new pathways for understanding the universe. This theory emphasizes that our experience of temporal flow might not reflect the deepest reality, but instead emerge from timeless building blocks and their relations. The philosophical and scientific exploration of this idea continues to evolve, as researchers attempt to identify what these fundamental non-temporal entities might be and how exactly they give rise to time. Whether ontological reductionism ultimately succeeds in fully explaining time remains an open question, but its influence on contemporary thought is undeniable. As we move forward, it becomes crucial to examine the ways in which ontological reductionism intersects with consciousness and perception. Understanding the role of the observer in constructing time could illuminate why time feels so real, even if it is not fundamental. This leads us naturally into the next topic, neuroscientific delay of perception. How the brain's processing creates an experience of time that may be disconnected from objective reality. Our experience of time, so seamless and continuous, is actually a product of complex neural processes that introduce subtle but important delays between external events and our conscious awareness of them. Neuroscientific research reveals that the brain does not register events instantaneously. Instead, sensory information travels through various neural pathways, is processed, integrated, and interpreted before it reaches conscious perception. This delay, often measured in tens to hundreds of milliseconds, means that our conscious experience of the present is always a slight reconstruction of the immediate past rather than an exact snapshot of real-time reality. This neural lag challenges the intuitive notion of a direct, immediate experience of the now. What we perceive as happening in the present is actually our brain's best attempt to synchronize various sensory inputs and make sense of them in a coherent timeline. This reconstruction is necessary because sensory inputs, light, sound, touch, all arrive and are processed at different speeds. To create a unified, continuous perception, the brain integrates this asynchronous information, often predicting or interpolating data to minimize the effects of delay. As a result, the brain generates a subjective experience of time that, while remarkably accurate and functional, is slightly offset from external events. This delay in processing and integration supports the idea that time as experienced is a constructed phenomenon, arising from how our neural architecture handles information. Our perception is not a transparent window onto an objective temporal flow, but rather a sophisticated cognitive interpretation designed for survival and effective interaction with the environment. For instance, slight delays are compensated for by predictive mechanisms in the brain, allowing us to react to stimuli as if we were experiencing them in real time. Moreover, the brain's processing delay introduces interesting paradoxes when we consider how we perceive causality and simultaneity. Experiments show that under certain conditions, our perception of the order of events can be manipulated or confused, illustrating that the temporal ordering we experience is malleable and dependent on neural computation rather than objective reality. This phenomenon emphasizes the potential disconnect between the physical progression of time and its subjective perception. Neuroscientific delay also contributes to the illusion of temporal continuity. Despite discrete processing of sensory information in bursts or frames, we perceive our environment as continuous and flowing. This smooth perception is a constructed narrative by the brain, stitching together discrete moments into a seamless experience. Thus, what we interpret as the continuous passage of time is a cognitive artifact, not an inherent property of the external world. This insight into the neural basis of temporal perception also impacts our understanding of consciousness and self-awareness. The brain's ability to create a coherent sense of time is fundamental to constructing a continuous sense of self, identity, and agency. Our narrative self depends on integrating memories of the past with predictions of the future, all anchored in the present moment as constructed by neural processes. Importantly, the delay in perception challenges the notion that consciousness operates in the immediate now. Instead, consciousness is always a little behind, interpreting what has already occurred. Philosophers and neuroscientists debate whether this delay implies that free will and conscious decision-making happen after the brain has processed information, not simultaneously with it. This has profound implications for understanding human experience, responsibility, and the nature of reality. Further evidence for the constructed nature of temporal experience comes from studies of temporal illusions, such as the flash lag effect, where moving objects appear ahead of their actual position due to processing delays. These illusions demonstrate how the brain's interpretation of time can diverge significantly from physical events, reinforcing the idea that time as we perceive it is a mental model shaped by the brain's architecture. Additionally, the phenomenon of post-diction in neuroscience shows that the brain can retroactively modify the perception of earlier events based on later inputs, further complicating the linear model of temporal experience. This suggests that our sense of when events occur is flexible and dynamically constructed rather than fixed by an external clock. These neural mechanisms highlight the intricate interplay between sensory input, neural processing, and conscious experience, informing our subjective sense of time. They also raise questions about the extent to which our understanding of time is shaped by biology and cognition rather than by objective, physical processes. The neuroscientific delay of perception thus offers a powerful argument for the illusory nature of time as we experience it. It supports broader philosophical and physical theories that question the fundamental reality of time, suggesting instead that time may emerge from the ways living organisms interpret and interact with their environments. Understanding this delay also has practical implications in areas such as human-computer interaction, virtual reality, and neurological disorders, where manipulating temporal perception can profoundly affect experience and behavior. It underscores the importance of considering the brain's temporal processing when designing technologies or treatments involving perception and cognition. In summary, neuroscientific evidence reveals that our experience of time is not a direct reflection of the external world, but a constructed phenomenon subject to neural delays and interpretative processes. This reinforces the notion that time, as we know it, might be more a feature of our minds than a fundamental aspect of reality itself. The implications of this view encourage us to reconsider how we relate to time, shifting from seeing it as an external constant to understanding it as a dynamic, brain-based construct deeply intertwined with perception, cognition, and consciousness. This insight naturally connects to related philosophical ideas about the continuity of experience and how the brain creates the illusion of a flowing present. Even though our underlying reality might be timeless or fundamentally different for what our senses suggest. With this foundation laid by neuroscientific studies, we can explore how the illusion of continuity arises in perception and cognition, which is the next topic, illusion of continuity, how discrete moments in time are perceived as a seamless flow. Our perception of time as a continuous, unbroken flow is something so fundamental to human experience that it feels undeniably real. Yet, digging deeper into the workings of the mind and brain reveals that what we actually experience is an illusion of continuity, a carefully stitched together narrative built from a series of discrete snapshots or frames. Much like a film reel, which is actually a sequence of still images played in rapid succession, our conscious awareness creates a seamless stream out of momentary slices of sensory data. This construction is essential for making sense of the world, but profoundly changes how we understand the nature of time. Cognitive neuroscience has shown that sensory input arrives in bursts rather than as an uninterrupted flow. The brain processes these bursts, or quanta of experience, individually, and then integrates them to form the impression of smoothness. This means our subjective experience of now is actually a composite of multiple moments strung together. The mind fills in gaps, smooths over discontinuities, and blends sensory impressions to maintain an uninterrupted sense of reality. One way this illusion is formed is through a mechanism called temporal integration, which collects sensory inputs over brief intervals and synthesizes them into a unified perceptual moment. This integration window might last tens or hundreds of milliseconds, during which incoming signals are combined, edited, or even slightly delayed to produce a coherent snapshot. Because these snapshots are updated rapidly, we do not perceive the underlying discreteness. Instead, we experience a smooth, continuous stream of consciousness. This process explains certain temporal illusions, such as the phi phenomenon or beta movement, where we perceive continuous motion between separate stimuli flashed in succession. Our brains do not simply record raw sensory data, but actively interpret and create a flowing narrative to explain changing stimuli. This narrative is essential for survival, enabling us to anticipate motion, predict events, and react fluidly in dynamic environments. The illusion of continuity also extends beyond vision to other senses and cognitive functions. Auditory perception, tactile sensations, and even memory rely on similar stitching processes. In language processing, for example, discrete sounds and words are seamlessly blended into coherent sentences and thoughts. Our sense of time, therefore, is a product of a complex, multimodal integration system rather than a direct apprehension of a physical temporal dimension. From a philosophical perspective, this understanding challenges the assumption that the passage of time is a fundamental feature of reality. Instead, time as experienced may be an emergent phenomenon arising from the brain's interpretive activity. This aligns with theories that posit time as a mental construct, not an external entity. Our experience of past, present, and future could be seen as the mind's way of organizing discrete experiences into a comprehensible order. Moreover, the illusion of continuity intersects with the idea of temporal granularity in physics and philosophy. The suggestion that at the smallest scales, time may not be smooth and continuous but quantized or fragmented. If time itself is composed of discrete units, then the brain's role in creating the appearance of flow is even more significant, potentially bridging gaps in the fabric of temporal reality. This insight has been supported by experimental psychology, where researchers have demonstrated how manipulations of sensory timing can disrupt the perception of continuity. For instance, slight delays between stimuli can cause viewers to notice breaks or flickers, revealing that continuous perception depends heavily on precise timing and integration in the brain. Additionally, neurological conditions provide evidence for the brain's role in constructing temporal experience. Patients with certain types of brain damage or disorders often experience distortions in time perception, such as time seeming to slow down, speed up, or fragment. These clinical observations highlight that continuity of time is fragile and heavily dependent on intact neural processing. The illusion of continuity also plays a vital role in our sense of identity and consciousness. The brain's construction of a continuous self through time, binding past memories, current perceptions, and future expectations, creates the impression of an enduring I moving through a temporal dimension. Without this stitched narrative, our sense of personhood and agency would be fragmented or lost. Furthermore, this perspective helps explain the phenomenology of flow states, where individuals feel completely immersed and lose track of time. In such states, the usual temporal markers and segmentation may become altered or suspended, reinforcing that our experience of time depends on the brain's active framing and interpretation. In literature, art, and subjective experience, the illusion of continuity allows for rich narratives and temporal complexity. Stories unfold linearly or non-linearly. Memories overlap with imagination, and the mind freely navigates temporal sequences, all grounded in the brain's ability to weave discrete moments into a coherent, flowing tapestry. At a deeper level, understanding the illusion of continuity prompts us to reconsider how we relate to time in daily life. It invites mindfulness of the constructed nature of temporal experience and opens philosophical inquiry into whether time itself flows or whether the flow is a cognitive artifact. Technological applications, such as virtual reality and video games, exploit this illusion by creating immersive environments where the brain's stitching mechanisms are engaged to produce believable continuous experiences. Understanding how the brain constructs continuity is crucial in refining these technologies to enhance realism and immersion. On a broader scale, this idea has implications for the study of consciousness and the mind-body problem. If our sense of temporal flow is a mental construction, then exploring the neural and computational bases of this construction may illuminate the nature of conscious awareness itself. Ultimately, the illusion of continuity does not negate the existence of time, but redefines it as a phenomenon arising from the interplay between brain, body, and environment. This nuanced view bridges the gap between subjective experience and physical reality, suggesting that time, as we live it, is as much a creation of the mind as it is a feature of the cosmos. As we move forward, it becomes clear that time's apparent passage depends on the brain's remarkable capacity to interpret discrete sensory data and weave it into an unbroken narrative. This cognitive feat forms the foundation of our lived experience, our memories, our plans, and our very sense of being. Having explored the illusion of continuity in perception, the next fascinating concept to examine is Einstein's block time. The idea that time is a spatial dimension and that past, present, and future all coexist timelessly. Einstein's concept of block time fundamentally challenges our everyday understanding of time by suggesting that past, present, and future are not distinct entities that flow or pass, but rather coexist in a four-dimensional space-time continuum. This idea stems directly from Einstein's theory of relativity, where time is not treated as a separate, absolute entity, but is intertwined with the three spatial dimensions, creating what physicists call space-time. In this four-dimensional block universe, all events, whether they have already happened, are happening now, or will happen in the future, exist equally and simultaneously. There is no privileged now, no unique present moment that objectively moves along a timeline. Instead, every moment is just another coordinate within this unchanging space-time manifold. Einstein famously referred to the common human perception of the flow of time as a stubbornly persistent illusion. According to him, the sensation that time flows from past to future is a psychological or phenomenological artifact, not a fundamental feature of physical reality. This insight upends the classical Newtonian notion of absolute time ticking away uniformly for everyone, everywhere. Instead, the structure of space-time and relativity is a fixed, four-dimensional block where time is just another dimension like length, width, or height. To grasp this, imagine a loaf of bread representing the entire universe. Each slice corresponds to a moment in time. In classical physics, the loaf might be sliced and served one piece at a time. Only the present slice exists at that moment. In Einstein's block universe, however, the whole loaf exists simultaneously. The past slices and future slices exist as fully as the present slice, even if we only experience one slice at a time due to our conscious perspective. Relativity further reinforces this view by demonstrating the relativity of simultaneity. The fact that two observers moving at different velocities may disagree on whether two events occur simultaneously or in what order. This means that what is now for one observer may be past or future for another, eroding the idea of a universal, objective present moment. The consequence is that the division of time into past, present, and future is relative, dependent on the observer's frame of reference. In this framework, the flow of time is not a property of the universe, but an aspect of human consciousness. Our experience of moving through time is linked to our psychological and neurological processes rather than an external reality, moving through moments. The block universe model thus aligns with the idea that the past and future are just as real as the present, contrary to the intuition that the past is gone and the future yet to come. This interpretation raises profound philosophical questions about determinism and free will. If the future already exists in the space-time block, does that imply everything is predetermined? Are our actions and decisions fixed and unalterable? Some argue yes, suggesting a frozen universe where all events are laid out and inevitable. Others suggest that the block universe does not preclude freedom, but requires a new understanding of it compatible with timelessness and relativity. Moreover, block time challenges the traditional notion of causality as a temporal sequence. While cause and effect still apply locally within light cones, regions of space-time influenced by a given event, the entire structure exists timelessly, making the idea of causes preceding effects less straightforward. Instead, causality is embedded in the geometric relations of events in space-time, rather than a sequence marching forward in an absolute time. Physicists use the block universe concept extensively in relativistic physics and cosmology, as it elegantly unifies space and time into a single entity, facilitating calculations and predictions about gravitational fields, black holes, and cosmic evolution. It also underpins the mathematical models used to describe the universe at large scales. Despite its success in physics, the block universe view remains counterintuitive and difficult to reconcile with subjective experience. Our consciousness seems irreversibly tied to the present, and the flow of time feels undeniable. Yet, many researchers believe this discrepancy highlights the distinction between objective physical reality and subjective phenomenology. The block universe model also invites reconsideration of how memory and anticipation fit into time structure. Memories are fixed records of past slices within the block, while future events exist as equally real coordinates we have not yet experienced. Our minds effectively move along the time dimension, though physically all moments coexist. Furthermore, block time intersects with other theories of timelessness and emergent time. Some interpretations of quantum gravity attempt to reconcile block universe ideas with the dynamic, probabilistic nature of quantum events, suggesting that the classical block is an approximation arising from more fundamental timeless laws. In popular culture and philosophy, the block universe has inspired numerous works exploring themes of fate, time travel, and the nature of reality. It reframes questions about whether time travel is possible, not by moving into the past or future, but by navigating the existing space-time landscape differently. Interestingly, the block universe also offers a way to understand phenomena like time dilation and gravitational effects on time. Since all moments exist, differences in experience time result from the geometry of space-time and the paths observers take through it, rather than time itself speeding up or slowing down. To summarize, Einstein's block time presents a revolutionary view of time as a dimension on par with space, where past, present, and future are equally real, and the flow of time is a psychological construct. This conception dissolves the absolute present, redefines causality and determinism, and invites profound reflection on how we understand reality and consciousness. Next, building on the idea of time as a spatial dimension, we explore the related but distinct concept of time as a spatial dimension itself, where time is literally another dimension in space, not separate or special. In many modern physical theories, time is treated not as a separate, unique entity, but as another dimension analogous to the three spatial dimensions we experience daily. This notion emerges most clearly in the framework of special and general relativity, where time is woven into the very fabric of the universe as the fourth dimension in what is called space-time. In this view, just as we can move forward and backward along the length, width, and height of space, time can be conceptualized as a coordinate axis, except that unlike spatial dimensions, it carries a distinct signature in the geometry of space-time. Treating time as a spatial dimension fundamentally alters our intuitive experience and understanding of reality. Instead of picturing time as something that flows or passes independently, this approach suggests that time is simply a coordinate we can use to locate events in the four-dimensional continuum. Events in the universe are identified by their position in space and their coordinate in time, combined into a unified description. This framework allows physicists to analyze and predict the behavior of objects moving near the speed of light or experiencing strong gravitational fields with great precision. One way to conceptualize time as a spatial dimension is through the mathematical representation of space-time as a four-dimensional manifold. In such a manifold, an event is represented by four numbers, 3 spatial coordinates and 1 temporal coordinate. While spatial dimensions are usually measured in meters, time is often expressed in units of seconds multiplied by the speed of light to maintain consistent dimensionality. This mathematical unification helps physicists solve complex problems involving gravity, motion, and the propagation of light. However, there is an important difference between time and space even in this unified model. Time has a distinct directionality or signature in the metric that defines space-time geometry. The metric is a mathematical object that tells us how distances are measured. In space, moving in any direction increases or decreases spatial distance. But in time, the metric introduces a fundamental asymmetry. Time-like intervals differ from space-like intervals. This difference manifests in how cause and effect operate and how observers perceive sequences of events. Despite this distinction, the fact that time is treated as a dimension alongside space radically challenges the idea that time is somehow fundamentally different or special. Instead, it encourages us to think of time as just another coordinate dimension, albeit with unique geometric properties. This perspective aligns closely with Einstein's block universe and the idea that all moments in time exist equally in a static four-dimensional structure. Conceptualizing time as a spatial dimension also invites fascinating questions about motion and location in time. If time is a dimension like space, could there be something akin to movement along it? In ordinary experience, we only move forward in time at a fixed rate, unlike spatial motion where direction and speed can vary. But in physics, objects are described as world lines tracing their positions in space-time. Our sensation of moving forward in time corresponds to following our unique world line from one coordinate to the next. Moreover, this approach implies that, like spatial dimensions, time can be curved or warped. General relativity famously demonstrates that massive objects bend space-time, creating gravity. This curvature affects both space and time, changing how clocks run near massive bodies and influencing the paths of particles and light rays. Thus, the shape of the time dimension is dynamic and influenced by mass energy content, which in turn affects the flow and measurement of time locally. Treating time as a spatial dimension has profound implications for how we understand causality and temporal ordering. Unlike space, where different points can be accessed independently, the time dimension is constrained by causality. Events can influence only those within their future light cones. This restriction introduces an arrow of time rooted in the geometric structure of space-time, preserving the notion of cause preceding effect, even though time itself is a coordinate dimension. This conceptual framework also interacts with ideas about time travel. If time is a dimension like space, theoretically, it might be possible to move backward or forward along it, much like moving through space. General relativity permits exotic solutions, such as closed time-like curves, which could allow time travel. However, Whether such solutions are physically realizable remains an open question. Furthermore, thinking of time as a spatial dimension inspires new interpretations of cosmology and the universe's origin. The Big Bang can be seen as a boundary in space-time, a particular slice or coordinate marking the beginning of a universe in time. Yet if time is a dimension like space, the nature of this boundary and what lies beyond it in time becomes a more nuanced question. In quantum theories of gravity, such as string theory and loop quantum gravity, time as a dimension becomes even more complex, sometimes emerging from deeper, more fundamental structures. These theories challenge the classical view of space-time, hinting that the smallest scales, the distinction between time and space, may dissolve or become probabilistic. Philosophically, considering time as a spatial dimension impacts how we think about free will, determinism, and personal identity. If the entire timeline exists as a fixed dimension, the flow of time we experience might be an emergent or illusory property, with profound consequences for how we view choice and change. This view also invites us to reconsider memory and anticipation. In a four-dimensional space-time block, the past and future are locations we can describe, but our conscious awareness is confined to a single slice or moment. Memory can be understood as accessing data from other regions of this block, while anticipation is mentally projecting forward to regions we have not yet experienced consciously. In summary, treating time as a spatial dimension reframes the entire concept of temporality, dissolving the classical idea of flowing time into a static geometric entity. It underpins much of modern physics and challenges deeply ingrained intuitions about change, progression, and existence. Now, building on this view of time as a dimension intertwined with space, the next theory, consciousness causes time, explores the idea that time itself might be dependent on consciousness, proposing that the experience of time arises only through a conscious observer. Consciousness causes time theory takes a radically different approach from many physical theories by placing the observer's mind at the heart of temporal reality. This idea suggests that time, as we know and experience it, does not exist independently out there in the universe, but rather emerges only when there is conscious observation or awareness. In other words, without a conscious mind to perceive and process events, time would have no meaning or even existence. This proposition ties together philosophy of mind, quantum mechanics, and metaphysics, raising profound questions about the relationship between reality and perception. At the core of this theory is the notion that consciousness is not merely a passive recorder of temporal sequences, but an active participant in creating the flow and passage of time. According to some interpretations, the linear experience of past, present, and future is constructed by the brain's interpretation of sensory data, memories, and anticipations. Without consciousness to slice reality into moments and order them sequentially, the distinction between before and after collapses, leaving a timeless existence. This perspective finds some resonance with quantum mechanics, particularly in interpretations that emphasize the role of the observer. The collapse of the quantum wave function, the process through which a quantum system's multiple potential states reduce to a single observed outcome, appears to depend on measurement or observation. Some theorists extrapolate this to suggest that not only quantum events, but time itself is dependent on consciousness performing observation, transforming a static, timeless quantum reality into a dynamic, temporal one. One of the striking implications of the consciousness causes time theory is that time's passage may be more a feature of subjective experience than an objective physical dimension. Just as colors do not exist independently, but arise from interactions of light with our visual system, time might similarly be a perceptual construct arising within the mind. In this sense, time is intimately connected to the emergence of self-awareness, memory, and intentionality. Philosophically, this theory aligns with various forms of idealism, which hold that reality is fundamentally mental or experiential rather than material. It challenges materialistic assumptions that place consciousness as a byproduct of physical processes and instead proposes a fundamental role for mind in shaping reality. Some advocates argue that consciousness could be the prime mover that generates time's arrow, sequentiality, and causality. Critics, however, raise concerns about the objectivity of this view. If time exists only when observed, what does that mean for periods when no conscious beings exist, such as before the emergence of life, or between observations in isolated systems? Does the universe freeze without observation? Supporters respond that consciousness might be a more ubiquitous property than traditionally thought, or that observation in quantum mechanics might include any interaction that causes decoherence, not only human consciousness. Neuroscientific studies shed partial light on this discussion by showing how the brain constructs a continuous experience of time from discrete sensory inputs. The mind stitches together events into a temporal narrative, and our awareness of the present moment involves integrating information over a short temporal window. This supports the idea that consciousness is deeply involved in shaping how time is experienced, if not in the fundamental nature of time itself. Moreover, experiments in cognitive science demonstrate that time perception can be highly malleable and subjective. Under various conditions, such as altered states of consciousness, meditation, or psychological disorders, the sense of time can speed up, slow down, or even disappear. This plasticity underscores the notion that time's flow is at least partially dependent on the workings of consciousness rather than an external absolute. From a physics perspective, the consciousness causes time theory raises intriguing questions about the interplay between observer and reality. Some interpretations of quantum mechanics, such as the participatory anthropic principle proposed by physicist John Archibald Wheeler, suggest that observers are integral to bringing reality into being. In this framework, the universe is not a fixed backdrop, but a participatory process where consciousness and physical phenomena co-create the temporal dimension. This theory also opens doors to deeper metaphysical questions about the nature of self, identity, and existence. If time depends on consciousness, then the flow of time might also be tied to the continuity of the self. Moments arise and fade as the conscious mind processes sensory input, forms memories, and anticipates the future. In this way, personal identity could be understood as a temporal construct emerging from conscious experience. Critically, the consciousness causes time approach invites us to rethink the relationship between physics and metaphysics. It challenges reductionist views that treat consciousness as an epiphenomenon and pushes toward more holistic frameworks where mind and matter are interdependent. While still speculative and controversial, it provides a compelling alternative to purely physicalist accounts of time. Additionally, this theory resonates with ancient philosophical traditions that place mind or spirit as primary, which suggests that time and change are ultimately illusions projected by consciousness onto an underlying eternal reality. On the practical side, exploring time as a byproduct of consciousness could impact fields like psychology, neuroscience, and even artificial intelligence. Understanding how temporal experience emerges from mental processes could improve our grasp of memory disorders, temporal illusions, and the nature of subjective experience. In summary, the consciousness causes time theory proposes that time is not a fundamental external dimension, but a phenomenon that arises from the presence and activity of conscious observers. It reframes time as a mental construct intimately tied to awareness and perception, challenging classical notions of time as independent and objective. Though controversial and challenging to empirically test, this theory enriches the dialogue between physics, philosophy, and cognitive science, inviting profound reflections on the nature of reality itself. Next, exploring deeper quantum phenomena that challenge classical notions of time. The delayed choice experiments reveal how future measurement choices appear to influence past events, further complicating our understanding of temporal order and causality. Delayed choice experiments represent one of the most fascinating and perplexing challenges to our conventional understanding of time and causality. Originating from thought experiments proposed by physicist John Archibald Wheeler, these experiments delve into the fundamental nature of quantum particles, particularly photons, and how their behavior seems to defy the classical flow of time from past to future. At their core, delayed choice experiments demonstrate that decisions made in the present about how to measure or observe a quantum system can appear to retroactively influence the system's behavior in the past. This astonishing result destabilizes the classical concept of a unidirectional, linear flow of time and suggests a far more intricate and interwoven relationship between cause and effect. The original idea behind Wheeler's delayed choice experiment was a variation of the famous double-slit experiment, which shows that photons or electrons exhibit wave-particle duality. They behave like waves when not observed, creating interference patterns, but behave like particles when measured directly. Wheeler's twist was to delay the choice of whether to observe the particle-like or wave-like behavior until after the particle had passed through the slits, sometimes even after it should have decided its state. Surprisingly, the experimental results indicate that the measurement choice seems to retroactively determine how the particle behaved in the past, as if the future measurement influenced the past event. This phenomenon is deeply counterintuitive and challenges the classical notion that the past is fixed and unaffected by future events. If the outcome of an event depends on a future action, the very foundation of cause preceding effect is undermined, shaking the bedrock of classical physics and everyday experience. In this sense, time's arrow, the idea that time flows strictly from past to present to future, becomes blurred or even non-existent at the quantum level. The experimental verification of these concepts has grown increasingly sophisticated, involving quantum entanglement, beam splitters, and delayed measurements with increasingly rigorous timing protocols. Modern realizations of delayed choice experiments reinforce the idea that quantum systems do not commit to a definite history until measured, and that the notion of a fixed, objective past may be an illusion. The implication is that reality, at least at the quantum scale, is not a straightforward timeline, but a complex web where events are interdependent in ways that transcend classical time order. Some interpretations of quantum mechanics, such as the many-worlds interpretation, suggest that all possible outcomes exist simultaneously in branching parallel universes, thus avoiding retrocausality but maintaining a block universe perspective. Others, like the transactional interpretation, envision a handshake between future and past quantum states, providing a time-symmetric explanation for these puzzling phenomena. Still, none offer a fully satisfying resolution, leaving the door open to radical revisions of time's nature. Philosophically, delayed choice experiments encourage us to rethink the nature of temporal reality. If the future can influence the past, then the strict linear progression of time may not be a fundamental feature of the universe. Instead, time might be more flexible, relational, or emergent from deeper quantum processes. This invites connections to other theories we have discussed, such as the block universe or timeless physics, where past, present, and future coexist rather than unfolding sequentially. The implications of these experiments extend beyond physics into metaphysics and even free will. If present decisions affect past outcomes, the classical picture of an independent, flowing time underpins our intuitive sense of cause and effect may be incomplete. This raises questions about determinism, the nature of choice, and whether time itself is a construct of human cognition or a fundamental feature of reality. In addition to challenging the arrow of time, delayed choice experiments have practical consequences for quantum information and computing. They underscore the non-local, context-dependent nature of quantum systems and the necessity of incorporating temporal ambiguities into the design and understanding of quantum technologies. The idea that temporal order is not absolute complicates how information flows and is processed at the quantum level. Some researchers speculate that these temporal anomalies might eventually offer clues toward reconciling quantum mechanics with general relativity, helping to build a theory of quantum gravity. Since general relativity treats time as a continuous dimension intertwined with space, while quantum mechanics suggests indeterminacy and non-classical causality, delayed choice phenomena underscore the profound tensions between these foundational theories. From a neuroscientific perspective, delayed choice experiments emphasize that our conscious experience of time, linear, causal, and continuous, is a constructed interpretation imposed on a fundamentally non-classical quantum substrate. This aligns with psychological findings about the malleability of temporal perception and the brain's role in constructing a coherent narrative of temporal flow. The broader cultural and philosophical impact of delayed choice experiments is profound. They resonate with age-old paradoxes about the nature of time, found in philosophy and literature. Questions about fate and free will, whether the future is open or predetermined, and whether the past is immutable or subject to revision. In many ways, delayed choice experiments bring these abstract discussions into the realm of empirical science, forcing us to confront the limitations of our classical intuitions. Moreover, these experiments invite a reconsideration of how we teach and conceptualize time in science and education. They demonstrate that time is not simply a universal constant marching forward inexorably, but a subtle, multifaceted phenomenon that behaves differently depending on scale, context, and observation. This complexity enriches our understanding, but also humbles us before the mysteries of the universe. In conclusion, delayed choice experiments offer a window into the enigmatic quantum realm where the neat boundaries of past, present, and future dissolve. They challenge the classical concept of temporal order and suggest that the flow of time may be more of an emergent, observer-dependent phenomenon than a fundamental aspect of reality. As we continue to explore these mysteries, we must be prepared to revise some of our deepest assumptions about the nature of time, causality, and reality itself. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.